Next one.
Check, check. Okay.
Thanks.
Okay. Hi everyone. My name is Pluck. Thanks for coming to the probabilistic programming session. We have 5 really cool papers that we're going to hear about today. Starting out with who's going to be telling us about random variate generation with formal guarantees. Take it away, Faraz.
Okay, good morning, everyone. Thanks for the introduction, Alex. This is joint work with Wanya Lee, who was my postdoc and who's now a professor here in Korea at PostTech. So I will start the talk with an overview of random variate generation and the current state of the art in the field and motivate the problem. I'll briefly describe what our technical approach is, present some experimental results, and point to some future work. So in this talk, I'll be discussing probability distributions, and in particular, probability distributions over the real line. These could be continuous probability distributions, things like a Gaussian distribution or an exponential distribution. But they could also be discrete distributions, things like a Poisson or a geometric. But they could also be these sort of mixed type distributions, which are neither purely continuous nor purely discrete, right? So here, you could have a coin flip, and if it comes up heads, you might sample a Poisson, or if it comes up tails, you might sample a Gaussian. So we are agnostic to the actual type of distribution, so long as it is a probability distribution over the real line. Now, of course, there are many other types of distributions. I won't go through all of them, but they have broad applications and many relationships with one another. So, for this session, I don't need to motivate the need for these probability distributions. They have broad applications in many fields. In particular, for probabilistic programming, these are the basic primitives that we use to build complex probabilistic models, right? By composing these distributions to build more complicated simulations. And what I'd like to argue in today's talk is that we need reliable software abstractions and programming interfaces for interacting with these probability distributions, which, for the most part, don't presently exist. So let me just briefly describe what are some of the operations that we want to do with probability distributions. So formally speaking, a probability measure is a set function over the real line, right? So it takes some measurable set A, and it returns the probability of that set, which is a number between 0 and 1. The things we would like to do with a probability distribution are maybe sample a random variable, x, according to that distribution. We might want to compute the cumulative probabilities. What's the probability sort of you're between minus infinity and x, or the survival probabilities, what's the probability you're between x and infinity, or you might want to compute the quantiles of a distribution, right? What is the 98th percentile of my distribution of SAT scores, for example. These are the things, some of the key operations that we would like to do. And it's a theorem of mathematics that whether I give you a probability measure, a random variable, a cumulative distribution function, a survival function, or a quantile function, there's a sense in which they are all mathematically equivalent representations of that single probability distribution. And what that means is there are many theoretical relationships that we would expect to hold. So for example, the probability of the left tail, f of x, the cumulative probability, is the probability that your simulated random variable is at least x. Or the survival function is the probability your random variable is greater than x. Or the survival function is 1 minus the cumulative distribution function. This is because probabilities are additive and they sum up to 1. There's the theorem called the inverse transform theorem, which says if I have a random variable x, which is drawn according to my measure mu, that has the same distribution as simulating a uniform number between 0 and 1 and passing it through the quantile function. Okay, and then there's sort of push-forward measures, lots of these different relationships that we would like to hold. Unfortunately, however, in real-world software, because we are computing generally over floating point numbers, not over real numbers, these relationships don't hold. And so here what I'm showing are some functions in the SciP library in Python, where you have the RV, the CDF, the survival function, and the quantile function, otherwise known as the PPF. And in general, we don't have the relationships that we would expect, because they are computing over floats. The reason is that algorithm developers in the current state of affairs are building their random variate libraries based on the assumptions known as the real RAM model. Okay, so these are very nicely laid out in Luc Devroy's classic textbook, Non-Uniform Random Variate Generation, where you assume your computer can operate freely over reals and do these infinitely precise operations in unit time. Okay, which of course is not very realistic. So for example, let's just consider the GNU scientific library, where we have an exponential distribution over the real line. This numerical CDF x will roughly saturate at 17.3. So if I ask you what's the probability you're less than or equal to 17.3, it will be 1. But if you actually simulate a random variable, it can be as high as 22.18. So there's a clear gap between these two different representations. And the reason is that these floating point functions, x minus 1 and minus log 1p, are not exactly related in any theoretical sense on a finite precision computer. So we did a quick survey of many different libraries, and we found that there are lots of actual issues that people are encountering in practice. Well, an interesting one, for example, was that the geometric distribution in NumPy can actually return negative values. But we all know the geometric distribution is counting the number of coin flips until a success, so that doesn't make any sense. Other things like, on an exponential, you could have a point mass at 0, which on a real RAM, that would never happen, but in a finite machine, that's something you have to worry about. It can give you downstream NANDs. And these are known to cause theoretical problems in areas like differential privacy or cryptography, many applications, some citations on the slide. So of course, the problem here is that in the real RAM model, all of these representations of a measure are equivalent, but when you perform the numerical approximation, this diagram does not commute, right? So my finite precision implementations don't have any equivalencies that we would have in the real RAM model. So the proposal in our work is to roughly change the type of workflow that we have, which is rather than have a numerical implementation of all of the different functions of a probability measure, what we're going to do is we're going to have a single numerical approximation of the cumulative distribution function, and that will serve as the source of truth for our desired distribution. That's our spec. Once we are equipped with this spec, we will automatically synthesize a random variate generator, or different random variate generators, with different properties, but ultimately all of them will be exact and equivalent to the specified CDF. And from that CDF, I can also get the survival function, the quantile function for free. So we want this very unified representation for our measure rather than this ad hoc one. So how does this work in practice? So here's the interface from the GNU scientific library, where I've renamed some of the functions for clarity, but they actually have 4 different algorithms for generating a Gaussian. There's the inverse transform method, the Box-Muller method, the ziggurat method, the ratio method, and they all do different things, right? Because they're all different numerical approximations. The GNU scientific library also has 3 different functions for computing the survival probabilities, the cumulative function probabilities, and the quantile, which also don't agree with one another. So I have these 7 different functions, all which do different things. The approach that we're taking here is more of a synthesis type approach. So you can see there on the final 3 lines, we could give the CDF and generate an exact sample from that CDF. Or we can give the survival function and generate a sample from that survival function. And I'll also show, it's a very powerful idea, is combining the survival function and the cumulative distribution function to come up with something called the dual distribution function, which is an extended accuracy representation that combines both the CDF and the survival function to represent more values, leveraging some of the limitations and strengths of floating point. But that's the general idea that we have here. So what does this buy us? Let's look at a simple example for the uniform distribution between 0 and 1. The traditional way to simulate a random number between 0 and 1, almost every library does this, is you generate a random integer I, which is between 0 and rand max, and then you'll just divide it, maybe by rand max or rand max plus 1, but this is well known in the literature to have many theoretical and practical problems. You can see clearly there are gaps, you don't get full coverage, and they're also not really uniform probabilities. I have 2 bins over there which have more probability than it seems that they should, right? So there's a paper by Goulart in 2020 which looks at all of the undesirable properties of this baseline generator. Using our approach, what you instead do is you give me the floating point function that defines the CDF that you want. For a uniform distribution, that's just the identity function between 0 and 1. So there's a uniform CDF. I write it in 3 lines of code, and then I generate from that CDF, which gives me full coverage of all the floats with the exact correct probabilities. Now, I will say for this very special distribution, there are many known methods to do it, but what's interesting here is you can do it sort of in a very automated way. And it also generalizes to non-uniform distributions. Okay, so that's a quick illustration. More generally, what are the benefits of the approach? Well, we can automatically synthesize random variate generations given their formal specifications that will all agree with one another. I'll also briefly show that these generators we build are optimal in a very strong sense. They are only consuming the information theoretically least random number of bits to generate an output. So they are actually very efficient in practice. And their distribution matches the formal specification. In terms of the accuracy, I'll also show at the end that we can cover a much broader range of values using our synthesis approach as compared to using the direct approach of implementing random variate generators. Okay, so let me briefly touch on the technical approach. I won't get too into the details, but just give you a high-level overview of what's going on. What we're doing here is we're going to remove the real RAM model, which assumes your entropy source gives you a real number and you transform it to a finite precision model, where your entropy source is giving you unbiased coin flips, and your random variable, your random variate, is a map from some finite string of coin flips to a string x, which is an n-bit string representation of some number. Could be a floating point number, a fixed point number, a posit number, a rational number, as long as it's a finite precision representation of that number. And all of the computations inside the box called random variate will also be finite precision operations. Now, what's really nice about this model is we have a unified representation of any random sampling algorithm in terms of an automata-like structure or a decision tree-like structure called a discrete distribution generating tree. And here's how it works. Suppose I have a discrete distribution over n outcomes, p1 through pn. In this case, it's a fair dice with 6 faces. The algorithm would roughly start at the root, obtain a coin flip. If it's a 0, it goes left. If it's a 1, it goes right. And it keeps repeating this process until it hits a leaf. So that leaf shows you the outcome. And there are some back edges because there's 8 outcomes, but only 6 of them I care about, so there's a little rejection loop here. Right? And you can also express that formally using the syntax of the function f. Right? So this is sort of a general model for any random variate generation algorithm in the random bit model. Now, if I have a DDG tree, the 2 things I care about are what its output distribution. You can simply find that by summing over all the leaves with a given label, multiplying it by the depth of the leaf. And you also care about what is the entropy cost of a distribution, what is the average depth of a leaf, right? Because that's dictating what is the runtime of the algorithm. How many coin flips do I need to hit a given leaf? And so a goal, once you're in this setting, would be for a given distribution, p1 through pn, I'd like to find a DDG tree, t star, that has my output distribution, so it agrees with the given probabilities, and it also has the minimal entropy cost to ensure that it's actually efficient in practice. So there's a general theorem from Knuth and Yau, a classic theorem, which gives a constructive procedure to build an entropy optimal DDG sampler for any list of probabilities, discrete probabilities. The details aren't important, but the key idea is that you write out all of the probabilities in binary, and then you build a tree based on these binary expansions. You put a leaf at a given level only if the bit in that corresponding binary expansion is a 1. So it's a constructive procedure, and so this is basically a solved problem. But it doesn't solve the current problem that we're thinking about today for 2 reasons. The first reason, the challenge, is that even if I have a small number of outcome n, this tree can be exponentially deep. This is something we showed in Popple around 5 years ago. But even more significantly, for the setting we're considering today, I formalized the random variate generator as a distribution over k-bit strings. But if there's 2 to the k of them, right? So if they're floating point strings, there's 2 to the 64 of them. So the number of leaves in the tree will be very large. So it's intractable in these 2 very specific senses. We can't hope to construct the entire tree. So what we do in this work is we introduce a different representation of probability distributions. So you have a CDF, f, here, which is a function between 0 and 1. What we're going to do is we're going to change our representation to something called a binary coded probability distribution, which is an alternative representation that maps finite length bit strings to 0 and 1, subject to the property that the probability of the empty string is 1, and the probability of any string b is going to be broken down into the probability of that string followed by 0 plus the probability of that string followed by 1. So roughly what we're doing here is we're representing a hierarchical partition of the real line and representing the probabilities of those partitions. So here's how it works. For the empty string, epsilon equals 0, Obviously, the measure is 1. For epsilon, for the strings 0 and 1, I've broken the interval in half, and the probabilities of each of those buckets are shown on the y-axis, right? So I can repeat this process to get more and more refined partitions. But what I'm doing is I'm lazily representing the probability distribution, whose probabilities now are shown on the y-axis, right? And so given this particular representation, what I might like to do is sample a string according to these particular probabilities shown on the y-axis, the width of those intervals. Okay, and then I can map any of those strings to an interval of the real line or any point in that interval that represents the outcome, the realized outcome. And what's really nice about this approach is that it also works if I've partitioned the x-axis using any number system. Nobody said it has to be uniformly spaced. They could be floating point numbers, they could be unsigned integers, they could be fixed points, so it's a very general representation for these partitions of the real line. Okay? So obviously, a naive baseline to do this is known as conditional bit sampling. You just use the chain rule of probability. You first sample whether you're in the left or the right over here, and then you sample, maybe if you're here, you would sample according to these two probabilities, et cetera, just using the chain rule of probability. But this turns out to be highly suboptimal if you implement it in practice, okay, both in terms of the space, the runtime, and the entropy. And I'll show some comparisons later on. So our first contribution in this work is that we actually give an entropy optimal random variate generator for any binary coded distribution. And I won't go through the details of the algorithm. You can see it's quite short. But it's lazily exploring one of these exponentially sized DTG trees that I mentioned earlier. Okay? And its correctness proof leverages the analytic properties of the real numbers. Okay? So it's quite subtle to get this to work well. And what's also interesting is that it's optimal in 3 senses. It's optimal in space, it's optimal in time, and it's also optimal in terms of the entropy that it consumes. Roughly what it's doing here is it's exploring only a single path down an exponentially sized DTG tree. Right? So it's similar to the chain rule of probability, but it's using a different property based on the binary expansions of the numbers, not on the sequence of conditional probabilities. So at each recursive level, I'm sampling 1 fresh bit using those lazy expansions. Okay, that's only part of the story, because I started the talk by saying, well, you know, in floating point, we have to be very careful about these issues, right? So here, I might have a CDF on 0, 1, which is x squared. So that's a vanilla CDF, because it's increasing and it's monotonic and all that. But if I implement in a floating point, it's actually a discrete function, right? I only get these black points. I don't get the infinitely precise curve. So what we also do is we give a floating point implementation when the probabilities of this binary coded distribution are floats, not real numbers. And it uses a fast integer arithmetic, and it only uses the same precision as the floating point system. So it only uses, say, 64-bit precision if you're on a 64-bit, if you're representing probabilities using 64-bit numbers. There are some technical challenges that are needed here, like, you know, we need the binary expansions of the difference of a pair of floats, even though that difference itself is not a float. So we need to develop an efficient algorithm for finding these binary expansions using fast integer arithmetic rather than arbitrary precision arithmetic to do this sampling in real time. So those details are in the paper. The final thing I'd like to point to in terms of the contributions is what I showed earlier in the talk based on the idea of combining a survival function and a cumulative distribution function. The idea here is that the probabilities in the floating point range 0, 1 are very precise near 0, but they're not precise near 1. Okay? This is a property of the floats. So if I look at the tail probabilities or the survival probabilities, they're very accurate near 1, but not accurate near 0. So what we can do is we can combine these to come up with what's known as a dual distribution function that's both accurate near 0 and accurate near 1. And maybe, you know, less accurate in the center, but it retains that symmetry. So for example, for the Rayleigh distribution, just, you know, one distribution you may not have heard of, or you may have, if you look at the CDF, it can represent a very small number near 0, but only 8.65. But if you look at the survival function, you can represent a number far from 0, but, you know, 38.6. Combining the two, we can get an extended range based on the idea that you're sort of focusing on the high precision regime. So here's a picture for how this works. You know, you have a cumulative distribution function f, which is increasing, a survival function s, which is decreasing. We find the median, the cutoff point, and we only focus on the probabilities in the lower half and throw away all of the probabilities in the higher, in the lower precision region, which are above half. Okay? And we also show how to do this sampling for a distribution function that combines these two representations. Okay, so I have around 2 minutes left. Let me briefly touch on some experimental results before wrapping up the talk. The 3 questions we're interested in are, in terms of these random variate generators, how are their performance in terms of the bits per variate and their variates per second compared to the GNU scientific library? How accurate are they? and what is the overhead of this extended accuracy method for generation that combines the CDF and the survival function. Okay, so here's a table. Obviously, I won't go through all the details, where I'm comparing the GNU scientific library, the baseline method based on the chain rule of probability and the optimal generator, and roughly in terms of the random bits per variate, where you want lower, we're sort of 3x more optimal than CBS and 142x more efficient than the GNU scientific library. In terms of the samples per second, we are faster by the conditional bit sampling baseline up to 10x, but we're currently a little bit slower, up to sort of a median of 6x, but all the way up to 35x as compared to the GNU scientific library. So there's some opportunity for optimization here. In terms of the accuracy of the generators, here I'm showing what is the width of the interval that you can cover using these different representations, right? So you should basically focus on how wide those colors are. Black is the GSL, and then green would be sort of the best method that we have. And just by visualizing, you can see that the green bars cover many more values as compared to the black bar. So you can cover intervals with a much wider range, up to sort of 10 to the 35x larger. The final question, which is what is the overhead of this method, roughly what we're trying to say here is that using a dual distribution function, the overhead is minimal as compared to only using a cumulative distribution function, using the optimal method, because we're not using arbitrary precision arithmetic. We're using finite precision floating point arithmetic, which scales very nicely in this setting. So they work well in practice. Okay, so there's a lot of future work here. I won't touch on everything, but I think there's still some opportunities to do some optimization using parallel or vectorized implementations. We'd like to integrate these primitives as part of an end-to-end verified PPL over floating point numbers, so taking it seriously, not just the primitives, but the whole composition, and doing sort of all these applications in differential privacy and cryptography and other areas that need sort of formal guarantees on the random variate generation. Okay, I'll just close with the contributions and maybe take a question. And there's also a code online if you'd actually like to play with these. So yeah, thanks for your attention, and I'll be happy to answer a question or two.
Yes, we have time for one question. Who has a question?
Cool. So I was trying to compare this to an alternative I had in mind. So if I want to sample from a Gaussian, to use your method, my first step is to write it down as the CDF of the Gaussian that I want to sample. But I was trying to imagine what the alternative would be if I wanted to use, say, the Box-Muller transform, and I could take my Box-Muller transform and change it to use finite precision arithmetic to get accuracy guarantees. And I was thinking that maybe I could get similar accuracy guarantees, but I would get a really entropy suboptimal sampler. So I suppose my question is, in this context, like how much does this entropy optimality really matter if I want to have like more samples but use?
No, that's a good question. Yeah, I think maybe one distinction here is that if you implement a Box-Muller transform, whether you're using floating point or fixed point, it's going to be intractable to compute the output distribution of that sampler, because that's a map from, say, the Box-Muller transform has a rejection loop, right? So you would need to map over all 2 to the 64-bit inputs to get a specific output. So you wouldn't have the same guarantees on the output distribution. You wouldn't know what the output distribution is unless you're using sort of very low precision, right? So in general, writing random variate generation code doesn't tell you what the output distribution is unless you're sort of using one low precision uniform number, like maybe 32 bits or 16 bits, et cetera. So I think it's not exactly clear to me what kind of guarantees you would ensure if you're doing pure generation code, rather than synthesizing a sampler that agrees with a given CDF. So I think you will still retain some intractability whether you're in fixed point or floating point. Yeah. Okay, it's your turn now. Thank you. Yeah.
Oh, what?
Yes,
Yes, I do. Wait. Hello? Good? Okay. Hi, I'm Jesse Michel. I'm a fifth-year grad student at MIT, and I'll be presenting semantics of integrating and differentiating singularities. Work with my phenomenal collaborators Wanyao Li and Hong-Suk Yang, who I think are here. Yeah. All right, so consider the program 1 over x. We might ask, what happens at x equals 0? And we get the famous divide by 0 error. And 1 over x is an example of a singular function, which is a partial function such that at 1 or more points, the left and or right limit diverge. So what if we take the integral of a singular function? We might ask, is the integral well defined? And the answer is no. And the reason is the way that you count area is by making these little rectangles. And if you draw a little rectangle around 0, it'll be unbounded, both below and above, right? So we're not going to settle for that, right? That's, you know, we can do something here. So what we're going to do is we're going to take an epsilon ball away, and we're going to say, hey, at least in this case, we can see the negative and the positive part cancel, right? So we should get 0 for every epsilon. And then we can take the limit as epsilon goes to 0. And this actually defines something called the Cauchy principal value integral, which is a singular integral. And it's defined exactly like this and is 0. All right, so this is a singular integral. And now we're going to take a look at automatic differentiation. So automatic differentiation automatically computes the derivative of a function. And it produces efficient derivative code because it preserves program structure. And there are these widely used libraries for automatic differentiation. And we can look at what standard automatic differentiation does for singular functions. And we'll get the same divide by 0 error at 0. All right, so now we're going to change this problem a little bit. We're going to add this parameter s in the denominator. And we're going to take the derivative of this integral with respect to s. And we'll get this result, right? OK. So we might ask again, is this well defined? And of course, the answer is no, right? You have infinite area in the shaded region. So it's not going to be well defined. But we're not going to settle for that. So instead, we're going to define something called the Hadamard finite part integral. And it's defined with limits sort of like the Cauchy principal value integral, except you have this lovely thing where you subtract this like 2 over epsilon term, which is sort of like getting rid of the infinity. You just kind of take only the finite part, get rid of the infinite part. OK, so one thing to note here is that the derivative of the Cauchy principal value integral is not equal to the Cauchy principal value integral of the derivative. But it is equal to the Hadamard finite part integral. All right, so it might seem a little bit crazy, right? All these weird different types of integrals. But it actually fits into a more general theoretical framework, which is called distribution theory. And informally, a distribution is a generalized function that's closed under limits and generalized derivatives. So we could take the limit of this sequence to get this Cauchy principal value distribution. And then we can take the generalized derivative to get the minus Hadamard finite part distribution. And because this commutes, we can go the other way, take the sequence of derivatives, and get the Hadamard finite part distribution, right? So this is a more general framework, and it's actually not all ad hoc. All right, so you might ask, why does all of this matter, right? And the answer is really singular integrals are like integrals or derivatives in that they're modeling tools. And so their value is defined by how useful they are at modeling things. So they're useful for modeling problems in signal processing, aerodynamics, and mechanical engineering. And a lot of these problems have a setup where you have some parameters, you have some loss that says how good your output is, and you do some gradient-based optimization. All right, so let's dig in to this aerodynamics example. And in this setup, you have a wing, And to make your plane fly, you need lift, right? And the way you can model this is you can slice the wing, right? So this little teardrop shape is a slice across the wing. And the goal here will be to calculate something called the circulation density, which relates to the lift. And it says basically, how is the wind spinning at a particular point? And you can model this problem with a singular integral, this Cauchy principal value integral. And the unknown is this gamma in the numerator. And the other parameters are these physical parameters. And one way to solve this problem is with these physically informed neural networks, where we approximate gamma with a neural network, gamma tilde theta. And then we have a loss that's basically for a bunch of u-naughts, we're going to take the difference between the left-hand side and the right-hand side squared, so that at the minimum of the loss, the equality holds. All right, so just a little bit of story. So we were working on these problems with singular integrals, and we were trying to write some formalism. And we had some trouble with the math literature, getting something to the level of rigor that we wanted. So we ended up putting a fair amount of work into building up the theoretical foundation. And I think there are some, at least results we couldn't find in other places. So, and this presentation also only uses like the tools of calculus. It should be accessible. And then once we put the math foundation in place, we define the first semantics of a differentiable, or of a programming language with singular integration. It also is differentiable. And we solve some problems in science and engineering. All right, so let's look at some code for how to implement this in our language singular flow. The main sort of features to highlight, you have finite iteration, you have singular integration, and you have automatic differentiation. So now you might wonder, how do we run this integral, right? And so remember how the negative and the positive parts canceled out. So the idea behind the sampling algorithm is you take a sample from the positive part, and you reflect it across the singularity. So they kind of cancel out. It's an algorithm to estimate that. And then you might ask, what happens when we run this code? Well, you have loss that converges. And if you were to do something like Monte Carlo integration on this problem, you would get a bad answer. And then you can look at the final circulation density in this problem, and you can see it matches by hand math approximation you can do pretty closely, which means that it's doing something sane. Now you can, OK, so we've solved this problem. And you can also apply the same technique to different shapes of airfoils, right? Different airfoil designs. And this sort of technique can also be used for solving inverse problems, like find the wing shape that will have the desired amount of lift, right? OK, so now I'm going to dig into the PL. We'll be pretty quick here. So expressions denote smooth functions. And programs denote a smooth map from context to context, right? So the denotation of this assignment statement just updates x with the denotation of e. And for integration, the key takeaways are that you have multiple notions of integration, right? So you can denote a regular integral, a Cauchy principal value integral, or a Hadamard finite part integral. And the key sort of technical result that you need to make the semantics work out, in particular to make sequential composition work out, is to have the result that the integral of this smooth function in the numerator, right, g, is smooth, right? So you end up with a smooth semantics, so you're closed. And the paper extends this to include if statements and finite loops, which adds a lot of fun complexity, right? OK, so that's the denotational semantics of this subset of the language. And we can go on to the operational semantics. And the idea here is you take in a context, a derivative context, which starts off as like a directional derivative, and an expression, or an assignment statement. And you update x, and you update x in the derivative, right? And you can do the same thing for this integration. primitive. And the key takeaways here are that you have separate estimates of the integral and its derivative. And maybe a non-trivial choice that we made and that we show is correct, produces correct results, is to reuse these samples. So just to reiterate, we had this result earlier that the derivative of the Cauchy principal value integral is equal to the Hadamard finite part integral, but it's not equal to just differentiating the sampler. So this sort of motivates doing, it's not as easy as writing your sampler and having AD take the wheel. All right, so you can see the paper for the full semantics, operational semantics, and a proof that that the operational semantics is an unbiased and consistent estimate of the denotational semantics. And then now just going back to the contributions, right? So we've talked about a little bit about the math, a bit about the formalism, and now we're going to talk about a few more applications. So we implement all of these applications in a little JAX library. We extend JAX with custom derivative, and the actual core implementation is just 100 lines or so of code to do that singular integration and to get the derivative correct. And now we're going to look at this Hilbert transform. So the Hilbert transform is much like the Fourier transform. It's a fundamental primitive in signal processing. And it's defined by this singular integral of a function. And we can just compare ground truth to ours, and the takeaway is they're equal. And we can note that standard Monte Carlo integration doesn't work well. And interestingly, Mathematica has support for principal value integrals and correctly computes the answers in this case, which I was excited to see. And then we can take the derivative. So this is also a useful quantity in signal processing. And again, we can see that ground truth and ours are equivalent. And if we just took the derivative of the Cauchy principal value, we get an answer that's like orders of magnitude wrong. And if we just do Monte Carlo integration, we get an answer that's also orders of magnitude wrong. And interestingly, if we take a look at Mathematica, it doesn't have a powerful enough symbolic solver to compute answers in these two cases. And it doesn't have a numerical solver out of the box. So we do a quick performance comparison. And the main takeaway is if you use JIT, right, the implementation is compatible with JITting, you get comparable performance. And if you don't, it's slower because there's stuff that the JIT compiler is able to optimize away that isn't optimized. All right. Now we're going to look at these crack propagation problems. So the idea is you have some material, we'll say like concrete, and it has a little crack under some force. And you might ask, how would that crack propagate? Right? So what is the crack displacement? And it turns out you can model this problem with a singular integral equation. So we have this Cauchy principal value and integral, this unknown sigma, another unknown sigma, and then the right-hand side, which is determined by the physical parameters. And we're going to use the same physically informed neural network approach to solve it. Right? You take the difference of the two, you approximate sigma with a sigma tilde theta neural network, and you find that the test loss converges and that the crack displacement that you get quite closely matches the ground truth, which you can laboriously calculate. And then we can also look at a 2D crack propagation problem. And this one has a Hadamard finite part integral in it. It's another singular integral equation. We can go through the same process and see that the loss converges, and you get a reasonable answer. So now I'm going to quickly talk about some related work. So there's these classic sort of math papers by Cauchy and Hadamard. There's the seminal work by Gelfand and Shilov. It's a big textbook on distribution theory that covers not these singular integrals with parameters in them, but singular integral operators. And then there are these numerics papers, one that has this symmetric sampling idea around the singularity, and a number of papers that study these finite part integrals. In particular, Monegato's 2009 paper. It's really great. I really like it. And of course, this work draws from a lot of PL work on the semantics of probabilistic programming languages and automatic differentiation with discontinuities. So to talk about some future work, there are these 3D singularities that come up in computer graphics. I really like both of these papers. The first one handles singularities by sort of thresholding. So saying if you took a sample and you got a value that was too big, just throw it away and don't look over there, right? And it works fine, but I believe, and I think the authors believe, that there's some opportunity to more accurately model this problem. And another one is this beautiful paper on the Kelvin transform, where you take a simulation of a PDE on an infinite domain, use the Kelvin transform to map it to a simulation on a finite domain with a singularity in it. You by hand handle that singularity, and then you solve the problem, right? So I think there's an opportunity here to automate this singularity handling. And also for both of these, there's an opportunity to do automatic differentiation, right? So if you can take the derivatives through these singular integrals, you can start solving inverse problems as well. So there's a lot of future work in this direction for the PL community, handling multiple singularities, more general singularities, nested integration, multivariate integration, more expressive control flow, support for higher order functions and recursion in the semantics. So in conclusion, we have the first language formalization for AD with singular integrals. There's a big need for more language features and more generality. And there are lots of exciting applications in PDE solvers, writing better PDE solvers with more automation, and to problems in computer graphics. And the open source implementation is here. And I'd like to thank Wanyal and Hongsuk again for all their help on the project. Thank you.
Thank you, Jesse. And we have time for a question. Yeah, for us.
Okay, good. Thank you for the talk. Very cool work. So one thing I noticed was the Monte Carlo variance was quite low in your experiments. Have you found areas where you're using Monte Carlo integration, right? Sampling to estimate the integrals. Have you found areas where the variance is too high? Maybe there's numerical instability, where you might need maybe a better estimator for the expectation rather than the naive Monte Carlo, using like importance sampling, or what are some opportunities there? Or are these all basically low dimensional problems where the uniform 0-1 generator that you showed is good enough? Thank you.
Right, so this is a great question. So there's a bunch of numerics work on making different samplers. We're using a sampler that's not the lowest variance. There are definitely opportunities there. And we show sort of 2 bits, like base 10, 2 bits of precision in our tables. But there are techniques that get, I think in King's book on the Hilbert transform, he gets like 10. So there's definitely a lot of room to be more precise in this problem. And we're also looking at single dimensional problems where doing like quadrature methods will probably significantly increase performance when they're tailored to the integrand. So I think there's a lot of opportunities there. And then in higher dimensions, I'm sure there's a huge amount of work that could be done there of making better samplers.
Thank you. Let's thank Jesse again. Our next talk is a remote talk.
Great. So next up, we have Qiancheng Fu, who's going to tell us about system called pressed with refinement session types that are probabilistic. Take it away, Qiancheng.
For instance, the classical deadlock problem of dining philosophers, there's a very simple randomized solution due to Rabin. And for race conditions, there's all sorts of for instance, algorithms based on leader election. And for lossy networks, there's all due to Rabin. Oh, there's no. Is there no audio? And for race conditions, there's all sorts of for instance, algorithms based on leader election. And for lossy networks,
I can hear you just fine, Qiancheng. Can you hear us?
oh, there's no.
Hello?
Is there no audio? Okay. So sorry. Lossy networks for retransmission, but these randomized distributed algorithms are hard to get right. It's hard to trigger and reproduce bugs. We can have lots of different kinds of silent errors where programs never crash, but they might produce wrong distribution of outputs. And this could lead to privacy and security risks. It's hard to. So that was the motivation that led to us developing the pressed language. So pressed, which stands for probabilistic refinement session types, allows for the embedding of probabilistic protocols into types. It features a message passing based concurrency, and it has a probabilistic semantics, and it formally guarantees that runtime behavior matches protocol. So the pressed language extends the probabilistic session types of Das et al., which was first presented at POPL 2023. So in probabilistic session types, we can write a session type like bool here. And what it is saying is that it's going to, on a channel, basically, this channel will send the message true with probability 0.6, and it will send the message false with probability 0.4. So this really defines an interface between a probabilistic client, between a probabilistic server and a client which relies on a probabilistic message. This restriction of probabilistic session types to concrete probabilities limits its expressiveness, as many real-life protocols are often parameterized by probabilities, and these probabilities may also evolve during execution. Pressed generalizes the concrete probabilities to symbolic probabilities. So here we have a p-bool type in pressed, which takes in a refinement variable p, which has to satisfy the constraint that it is greater than 0 and less than 1. And because if it satisfies this constraint, then we allow it to be used as a probability for annotating the true and false messages. So this is saying that we are going to send a message true with probability p and send the message false with probability 1 minus p. So these symbolic probabilities can both be universally and existentially quantified in the logic. This generalization significantly improves the expressiveness of pressed over probabilistic session types. To realize one of these probabilistic refinement session types in a process, a pressed features a flip primitive for generating randomness. So here we have the flip construct, and it takes in an argument p, which is just a refinement expression selected from the interval 0 to 1. And this flip construct says that it will land on heads with probability p. And if it does so, it will execute the code that is written in the heads branch. And it will land on tails with probability 1 minus p, and then execute the code inside of the tails branch. To type check a pressed process, the flip construct interacts with these probability refinements that we have in the types. So for instance here, we have defined a function called makePbool. And what it's going to do is it's going to try to implement a channel which communicates according to the pbool session type. So the idea here is that it's going to execute a flip, and in the heads branch it's going to send true, and in the tails branch it's going to send false. So if we look at the true branch, or the heads branch, we're sending on this channel the true constant. So if we look at this branch in isolation, the distribution of messages sent over this channel is actually just true with probability 1 and false with probability 0, because there's no possibility of false being communicated in this branch in isolation. Now, conversely, in the tails branch, we would have false be at probability 1 and true be at probability 0. Now that we know the distribution of messages in these two branches, we can compute the distribution of messages for the overall flip expression. And this is done by performing a weighted sum over these two distributions. And that gives us the overall distribution of the entire flip expression, which is true at p, false at 1 minus p. And then the press type checker will then go in and check that our computed distribution is equal to the one that is specified by the session type. And these kinds of constraints would be gathered by the type checker and then exported to an SMT backend for verification. And then the pressed type checker will then go in. So now that we've seen the basics of using pressed, I want to talk about modeling probability distributions in pressed. So many randomized distributed protocols require sampling from probability distributions. For example, we have leader election. We need to sample from a number of candidates. In crowd forwarding, we need to randomly sample from a crowd of nodes. In the zeroconf protocol, we need to sample from an IP address space. So now the question is, how can we accurately state these kinds of protocols in pressed? If we try to encode distributions like the uniform distribution from 0 to k, we face a conundrum because of this k here. K is just an arbitrary natural number, and this uniform distribution is essentially of arbitrary size. But our flip construct, it only has 2 branches, so it can only really give us 2 kinds of results. And our probabilistic types that we've seen before only have a fixed number of possible branches that you could take with some kind of probability. So this kind of creates an issue for us. But we have the key idea that we had to get around this is to actually let probabilities and the refinements interact. So here we define something we call the UNet type. And intuitively, the UNet type is trying to model a natural number that is uniformly sampled from the distribution 0 to n. And notice that in the UNet type, for the suck message and the 0 message, both of these are sent with a probability that is determined by the refinement variable n here. So UNet sends a suck message with probability n over n plus 1, and it sends a 0 message with probability 1 over n plus 1. So if we look at an example and we try to unpack UNet at a concrete value 3, we will find that a channel of this UNet 3 type will send the message 0 with probability 1 over 4. Because if we substitute 3 for n, we get 1 over 3 plus 1, giving us 1 over 4. For the message trace suck 0, we would actually have 3 over 4 times 1 over 3, because the first suck message comes out with probability 4 over 3, 3 over 4, and the 0 message comes out with probability 1 over 3. So the probability that these two events occur together is actually just 1 over 4. And similarly, if we have suck 0, the computed probability that this comes out is 1 over 4, and then 3 successors is also 1 over 4. So we can actually just conclude that UNet 3 encodes a uniform distribution over 0, 1, 2, and 3. And similarly, if we have suck 0, now our claim now is that the UNet n type encodes the uniform distribution 0, 1 to n. So this is very good news because at least we have something and we can verify this claim by hand using just induction. But the even better news is that we can actually automatically verify this using PREST itself. So this is a very surprising discovery. Basically, we discovered that these refinements allow us to encode probing processes to measure probabilistic properties. So here we have defined a function or a process called UNet PMF, which takes in 2 arguments, x of type UNet n. So this is just basically a uniformly sampled natural number from 0 to n, and a natural number y, which is just an arbitrary fixed natural number between 0 and n. And all that UNet PMF is doing, which I've elided here, is that basically given x and y, UNet PMF returns true if and only if x is equal to y. So all this UNet PMF is doing inside of it is it's just doing an equality comparison between x and y. But we know from basic probability theory that this is exactly the definition of a probability mass function, and that the UNet PMF, it returns true with the exactly correct probability you would expect from a uniform distribution. So the very fact that UNet PMF is well-typed tells us that the UNet type correctly encodes the uniform distribution, and we do not even need to run the UNet PMF function at runtime. So this entire verification procedure is completely static. So now that we have the UNet type, we can build on top of it much more interesting real-life protocols. So here we have a node in the crowd anonymization protocol. So for this node here, it has a refinement variable I, which is the identifier of the node, and a variable k, which represents the total number of nodes in the protocol. And at the start of the protocol, the node will receive a packet, which has a forwarding target of itself and a final destination of j. If the current node is the final destination of this packet, then we can accept it and then end the protocol. If the current node is not the final destination, then the node will repackage the packet, basically by discarding the target and resampling a fresh, uniformly chosen node as its new target, and then forward that out. So for the meta theory of PREST, we show that PREST possesses the following properties. It has type safety, evaluation of PREST programs preserves types, it has global progress, PREST programs are guaranteed to be deadlock-free. We have probability consistency, that the distribution of communicated messages at runtime always match the specification of these probabilistic session types. And we also have an expected cost bounds theorem that tells us that the expected runtime cost of a program is upper bounded by its cost specification. So in this talk, I did not introduce this cost analysis mechanism. So if you're interested in that, we go into more detail in our paper. So for implementation and evaluation, we implemented a PREST type checker in OCaml following a bidirectional type checking strategy. So this diagram depicts the general architecture of the type checker. So we have an infer procedure and a check procedure. And these two procedures produce large amounts of logical and probability constraints, which are gathered up and then shipped to an SMT backend for automatic verification. So we evaluate PREST on a wide array of benchmarks, and we have a backend using Z3 and a backend using CVC5. So despite these very nasty nonlinear real arithmetic constraints, Z3 tends to perform very well. All benchmarks are solved within 0.3 seconds. CVC5, on the other hand, is not as robust at solving these PREST constraints. They often time out because from what I understand is that CVC5 lacks some of these heuristics for Z3 to optimize these kinds of constraints. So for future work and conclusion, in the future, we would like to reason about cryptographic protocols and differential privacy. In fact, that is a project that we are currently doing right now. We want to improve constraint expressiveness and automatic solving with relaxed notions of satisfiability. We also want to integrate ideas from probabilistic program logics to enhance the expressiveness of the refinement logic that we're working with. So in conclusion, we develop PREST for specifying and constructing randomized distributed systems. The integration of probabilistic and refinement types allows for rich specifications and symbolic reasoning about protocols. PREST programs are formally guaranteed to behave according to their protocols. And a type checker for PREST is developed and evaluated on a variety of benchmarks. The PREST type checker performs well on many randomized protocols. So that's the end of my talk. So thanks to everyone.
Thank you, Qiancheng. Let's take a question for the speaker.
The PREST type checker performs well on many randomized.
Well, I have a question, Qiancheng, which is you showed this example where you used a probe program where its type told you something interesting about another program. That was a cool pattern. And I'm wondering, besides sort of probability mass functions that you can look at by sort of giving a type to an equality check, are there other sorts of probes that you found useful in your examples? Where its type told
Yes.
you something interesting about another program. That was a cool pattern. And I'm wondering, besides sort of probability mass functions that you can look at by sort of giving a type to an equality check, are there other sorts of
Yeah.
probes that you found useful in your examples?
Oh yeah, absolutely. So it depends on the kind of distribution that you want to verify. So the PMF was the easiest one for this particular example, but for verifying a distribution where we had the sum, or was it the max of two uniform distributions?
Oh yeah.
So
absolutely.
for that one,
it depends on
yeah. We used a cumulative distribution function for that example, and there was another example. I don't remember. I think it was the sum or something that we had. We actually had two functions that verify. One was verifying like the front of the distribution, and the second one was verifying like the second partition of the distribution. So you can really it's very it's very free as to what you do. It's just you just need to make sure that the implementation of these kinds of processes is sufficiently easy to see that it corresponds to like a cumulative distribution or a probability mass function. It's just you just need to make sure that the implementation of these kinds of processes.
Hello? Let's see. Oh, okay, I need to actually hook it up, of course. Is the microphone working okay? Cool.
Did you hook it up?
I am currently.
You're connected, right? Great. Okay, so this next talk is Maddie Bowers at MIT, who's going to be telling us about a new inference algorithm for discrete probabilistic programs. Take it away, Maddie.
All right. Hi, everyone. I'm Maddie Bowers, and today I'll be presenting on a new approach to inference in discrete probabilistic programs, which we've implemented in a language called Pluck. So the algorithm I'm going to tell you about today was designed to work with a quite expressive language. So for example, here's a function that generates random binary trees where each node holds a number. And in particular, this uses algebraic data types and discrete random choices, arbitrary recursion, and we support a whole bunch of other features, like higher order functions as well. Now, when the users define this program, there's a handful of different questions they might ask about it. For example, they can query the distribution of some expression in the language. So for example, here is an expression that samples a tree and then asks if its size is less than 4. And Pluck determines that this expression evaluates to true with probability 85%. Now, a user could also ask for something like the conditional distribution of some expression, given that some user-specified Boolean condition is true. Or, for example, we could generate samples from these conditional distributions. For example, here we condition our program on the condition that generates a valid binary search tree and sample from that distribution. Now, in order to support this kind of user experience, we want to handle this kind of expressive language and ideally provide exact answers when possible, but gracefully fall back on accurate approximations when we can't. And this is a really hard problem. A lot of existing languages have important drawbacks. So for example, exact inference in discrete languages frequently can't handle this kind of recursive tree generation program, which has infinitely many possible executions. And approximate inference algorithms often can't leverage the structure of the programs to actually leverage independence and do this efficiently. So they instead often fall back on like Monte Carlo algorithms that, for instance, would never randomly hit on a balanced, or rather on a valid binary search tree. And so our approach is going to build on a few ideas from the literature to derive a new algorithm that can actually deliver these capabilities. So the first of these ideas is laziness for efficient inference. And this is actually something that has been known for a long time. In fact, going back to some of the earliest probabilistic programming languages, like one developed by Daphne Koller and colleagues in 1997, relied on this insight. But in the past decade or so, laziness has mostly been abandoned in favor of approaches that exploit independence in a program with various static analyses. So in this work, we're going to be revisiting this idea of laziness in light of these recent advances in sophisticated inference. So first, let me show you why laziness can be useful for inference. Say we've written a probabilistic program perturb that takes a string and stochastically inserts typos. So for example, we might run this on the word lazy and get out words like lucky or lousy or hazy. And there are actually infinitely many possible strings that this could produce. Now, as a program, perturb is going to be a recursive function that takes an input string of characters, and either that input is going to be a nil, in which case it's just going to insert any number of characters, or the input's a cons, where we'll decide whether or not to keep that first character, we'll insert some number of characters, and we'll recurse on the tail of our input. Now, these helper functions, maybe keep and maybe insert, essentially do what you would expect. So maybe keep is going to stochastically decide whether or not to drop the first character, and maybe insert is going to stochastically insert a random string in front. And now, given a program like this, a natural question we might ask is, what is the probability of corrupting our string lazy to a particular output string, like lucky? Now, one approach to this is just to enumerate possible paths through our program, right? So for example, at the first step of perturb's recursion, we could keep the L and insert the word, or insert UC, or we could drop the L and insert the entire word, luck. Or we could, for example, drop the L and insert some other prefix, like SE. And continuing this process, we can build up the full 3 layers of the recursion in this example. And if we add up the probabilities of all of the paths that lead to lucky, then we have our answer. But there's an issue here, which is that this tree is actually infinite. And in fact, it's infinite even at the very first level, because we could decide through the recursive maybe insert function to insert a string of any length. Now, so standard enumeration is never going to terminate. But what if we adopt the lazy semantics here? So in the lazy semantics, we're going to thunk our arguments. And so we pass in these unevaluated thunks into our function. And now, with equality being the classic recursive implementation on lists, it's going to first check that the head of the list matches before recursing on the tail. And in particular, this means that right, as soon as a character doesn't match, we're just going to immediately return and not do this recursion on, on the thunk representing the rest of the string. And this means that laziness is effectively implicitly marginalizing over all of the possible, or all of the choices that are inside of those unevaluated thunks. They simply aren't part of the possible execution paths when you're viewing this lazily. And this is great. So for example, on this particular program, it actually brings us from an infinite tree down to a finite tree, because we're going to end up rejecting every execution path that has an incorrect prefix as soon as it produces the first incorrect letter of that prefix. And so this is great, but we actually still have an exponentially large tree of executions here. And the key issue is that we're running into a lot of the same subproblems, the same subtrees, again and again. So, and we'd really like to kind of merge these, which corresponds to exploiting the independent structure that's present in the probabilistic program, right? So there are multiple ways to get to the same intermediate state, and we really want those to not be fully represented again and again everywhere they show up. Now, this kind of structure is exactly what modern efficient discrete inference algorithms focus on. And in particular, we're going to be looking at one called knowledge compilation, a state-of-the-art technique for inference in discrete probabilistic programs. Now, this works by compositionally translating a probabilistic program into a representation of all the paths. And importantly, this representation is a graph that can capture exactly what we were looking for on the previous slide in the perturb example, where since it's a graph, intermediate states can be reached by multiple incoming paths. But standard knowledge compilation is strict. So for example, in something like let x equals E1 and E2, we're first going to compile E1, compile E2, and then combine these representations to get our overall expression compilation. And the same goes for function calls. So with something like equal perturb lazy lucky, we are going to attempt to compile our argument and end up just failing to terminate, because there are infinitely many ways that perturb lazy can execute. And so our approach is going to combine the benefits of laziness with these modern techniques of knowledge compilation. We're going to do this by making knowledge compilation lazy. So how do we do that? Well, when presented with an expression like this, we can thunk E1 and then go and compile E2, just compiling E1 on an as-needed basis if E2 ends up using it. And we can do this for functions and constructors. And with perturb, this means that we're going to thunk our arguments, so we won't attempt to do that big compilation up front. But there's a little bit more nuance to making this actually work in practice. So let's look at a simpler example. So here's a program that, in its first step, generates a list x's, which is a random number of random Booleans. And in the second step, it checks if every Boolean in this list is true. Finally, and finally it checks the length of this string, and if it is small, less than 4, then we end up returning B, otherwise false. And so here we're going to end up thunking x's and B, and when we get to this point in the program, we're going to end up forcing B, right? And if we just forced exactly what we thunked up there, then we would be out of luck. We would be attempting again to generate that infinitely large distribution. But here, we can actually leverage the fact that we have this path condition, right? And using this, knowing that X is only going to be a short list, we can compile conditionally, or rather, we can compile the conditional distribution of B conditioned on our path condition. So, and this, in general, is the key benefit of lazy compilation. So we're allowed to compile these conditional distributions of thunks, which can be a lot simpler than the full distribution. So in this case, it actually brings us from an infinite situation to a finite one. Now, there are actually some issues that come up with this when it comes to caching, because if the same thunk appears in multiple different path conditions, you don't want to have to compile it in every case, but you can't always reuse the same compilation result across every usage, depending on the path condition. So details of that are in the paper. We developed a technique called guarded caching to handle it. Now, one place where this kind of compilation is super useful is when dealing with compound data structures. So this is a very common pattern in probabilistic modeling where you have some observed structured data, and you have some model of your data that you can sample from, and you can check if these results are equal in order to see how likely your data is under the model. And in strict knowledge compilation, when we're trying to generate this structure representing all the ways that X could go, we have to end up representing full distributions for each of the elements of this list. And in particular, and these are really complicated distributions at times that have to encode dependencies between all these different elements. Now, for example, if we focus on X3, so in general, this is the situation with strict compilation, but with lazy compilation, we can actually do something a bit smarter. So when it comes to compiling X3, we actually know that equality has already checked that the first two elements were equal to their observations, right? So essentially, we get this path condition that tells us that X is 1 is 1, X is 2 is 3, and this can give us a much simpler distribution than we would have otherwise. And so, so what does this all buy us? Well, we've implemented lazy knowledge compilation in Julia in an open source language called Pluck, and we'll compare it to Alia, a Julia implementation of strict knowledge compilation based on the DICE language. Now, the first question that we're going to ask is, how do these approaches compare on classic benchmarks from the literature? So here's a log scale graph showing the ratio of runtimes of Pluck to Alia. So anything above the dotted line is Pluck doing better, and below is Alia. And first, we note that, there's a handful of programs where you can't take advantage of laziness, and so you're just going to get some overhead from the lazy approach. And in particular, on that first benchmark is the most dramatic one. We're around 28 times slower. This one is sort of a worst case for Pluck, where it's a big Bayes net, where the same thunks have to be forced across many different disjoint branches with disjoint path conditions. And so you end up having to do a lot of recompilation. Now, there are some benchmarks where there's minor benefit of laziness, and here we see some improvements of Pluck over Alia. But where laziness really shines is on these models of structured data, things like the perturb example from the start, probabilistic context-free grammars, generating sorted lists. In these situations, we end up going from taking, Alia takes seconds to around a minute, and Pluck finishes in milliseconds. So it ends up being around 1,000 to 10,000 times faster. Okay, so let's take a closer look at this scaling. Let's look at how we scale with respect to the size of the observations. Now, first, we find that there are some regimes where laziness is really key to scaling. So on this log-log plot of input size versus time versus input size, Alia scales exponentially, while Pluck and lazy enumeration scale polynomially. And conversely, there are other places where the independent structure that you can get with knowledge compilation, or that you can exploit with knowledge compilation, matters a lot. So here, lazy enumeration is not going to do well. It'll be exponential, and Pluck and Alia are similar polynomials. So Pluck can take advantage of kind of the best of both of these worlds. Now, additionally, for infinite distributions, on that previous, or in all of our earlier results, we had to, or rather, on the ones that are infinite, we had to give a recursion bound to Alia. And here's a plot of runtime versus recursion bound. And if you set it too low, it'll terminate quickly, but give you a wrong answer. And so we are very careful in this plot, or in our experiments, to set a bound that is just that is just high enough to produce the correct answer. But if you set it too high, you're going to end up scaling. Very poorly with the bound. And in contrast, something like Pluck is effectively inferring the bound for you as you go. You don't need to specify any bound. Laziness effectively, unrolls the recursion just enough. Now, for time, I'm going to skip over some of the rest of these results, but the full results are in the paper. We've also evaluated on randomly generated programs to look at the robustness to different ways of writing Pluck programs. We find that Pluck outperforms Alia. And finally, Pluck is also fast enough to run inside the loop of a program synthesis algorithm and can solve more problems faster than other methods. And again, the paper has full details for those experiments. Now, we've also open sourced an implementation of our algorithm in Julia, which you can check out here, complete with a tutorial, documentation, language reference, developer's guide. And so please try it out and let us know what you think. And additionally, the paper goes into detail on a few other things I couldn't cover in the talk. We have an approximate inference version of our algorithm that works when exact inference is too expensive. And we have a correctness proof based on the semantics of Dash et al. On the theory of lazy probabilistic programming. So find me at the conference. I'd be happy to chat more about any of this, and thank you so much.
Do we want to take one question, maybe? We're running a little bit behind, but yeah, for us.
Thank you for the nice presentation. I was curious, does Pluck ensure that the number of program paths is finite? Does the DSL ensure that? And if not, have you thought about ways you could get maybe upper and lower bounds based on enumerating path probabilities, which is something that people do in the literature? How would that interact with your system? Thanks.
Yeah, thank you. That's a great question. So right now, we do not automatically infer. So our DSL is very general and doesn't enforce that you're doing something that terminates. You can have a timeout and exit early, of course, but in the cases where, I'd say there are two things that you can do in the cases where it's not going to terminate. One is that the SMC version, or rather the approximate inference version of the algorithm that I didn't have time to talk about here, can be used in cases where there would be infinitely many executions, at least some of those cases. So that gives you a bit more flexibility. The other thing is, you mentioned the idea of getting bounds, and that's something that we've looked into a bit. We've worked with lazy enumerative approaches that sort of explore the path of traces in a kind of best first way to try to figure out as much of the probability distribution as possible. But we, I think, adapting that kind of thing to work with knowledge compilation is an area that we've thought a bit about but haven't completely figured. We would love to, yeah, I'd love to chat more about that later.
Thanks. Let's thank Maddie again. Okay, awesome. So next up, we have Cameron Moy, who's going to tell us about Roulette, which is a language embedded in Racket for expressive, exact, and efficient discrete probabilistic programming. Take it away, Cameron.
Thank you. There's actually going to be a lot of similarities with the last talk, so thank you, Manny. This is work done with Jack, who is in the room, John, Brianna, and Stephen. We're all at Northeastern University. So why another discrete PPL? It really comes down to, for us, these three adjectives: expressive, exact, and efficient. So let me say a little bit about what those are. So first of all, for a probabilistic programming language of the sort we care about, we want it to be extremely expressive. So what does that mean? It means that programmers should be able to program in a very natural style. In other words, to be able to write programs as if they were using a conventional programming language with all of the features that you might want from that. So that includes high order functions, mutable state, modules, but also might include some more unusual features like macros, say. So we would like that. That's the kind of most important aspect. But the other two are also important. One is that we're looking at exact inference. So the inference should give you deterministic and precisely correct results for all of your probabilistic queries. That's opposed to approximate inference, which is also very common. And we're also looking for efficient inference. So we would like it to be as fast as possible, and we would like to be able to scale to reasonably large programs. So we're not interested in just handling toy programs. We would like to be able to actually write large pieces of software and be able to perform inference. Okay, so we would like to be at the intersection of all of these three things. And so that's what I'm going to propose with some caveats, which I will get to at the end. Okay, so to motivate this a little bit more, let me give a concrete example. An example I'm going to give is of unreliable hardware. So suppose you're working at a company which is producing hardware that is going to go off into space and is going to be exposed to gamma radiation, for example. And there's going to be some probability of some errors. Maybe you perform an operation and it doesn't actually work correctly. So you would like to write a simulator for the scenario and run a program, say, through the simulator with a certain error rate. And you would like to see what's the distribution of results from that. OK, so how would you like to write that? Well, if you're a functional programmer, you might like to write it like this. Here's an implementation of a simulator, and it's written in a very high order style. Every single command is a function that takes in a memory and gives you back another memory. Memory is just represented as lists of bit vectors. Since we've written it in higher style, for example, you can see sequencing takes in two functions and composes them and threads the memory in the standard way. But what's interesting here, of course, is what happens when you do assignment. And assignment is going to be one of the operations which can be potentially faulty. And we see here, you might miss it if you're just looking at the code as a whole. You might think it's a regular scheme or racket program. But there's actually a flip in here. So with some low probability, instead of actually assigning to a variable, we're going to just zero it out. Okay? So suppose we want to actually run this on an example. So this piece of code is not particularly important. It's just calculating triangular numbers, but it's using the abstractions that I've defined on the previous slide. And here I'm going to be calculating the fourth triangular number. Okay? So we would like to simulate this. Here's an example of when the error rate is 0. And we get the fourth triangular number with probability 1, which is 10. And let me actually just increase the error rate a little bit, and you'll see that now we get some probability mass on some of the other answers. And then, of course, if I increase the error rate, we're going to get more probability mass on the others. And if I increase it quite a lot, then you can see we get a lot of noise out. Okay? So we would like to be able to run programs like that. So how do you do that? So we have a discrete probabilistic programming language called Roulette. And it brings together two ideas, which kind of are existing in the literature, but turns out that they work really, really well together. And that's kind of the big idea of this paper. So I'm going to give a bit of background on both of them. So the first big idea is to execute programs using a symbolic evaluation. So this is kind of a variation on symbolic execution, which I'll go into in a moment. And by executing programs in that way, you get concrete values, which are guarded by Boolean formula. OK, so what do you do after you get that? You can then perform inference by using these Boolean formula to calculate probabilities. And like the previous talk, we're going to use knowledge compilation to do that in a scalable way. OK, so let me talk about these two ideas and give some background on that. So the first is symbolic evaluation. This idea, there's some concurrent work, but the main piece of inspiration for us is the Rosette programming language, which is where the name Roulette comes from, which is a solver-aided host language inside of Racket for building DSLs which need solver-aided capabilities. And I should also like to say, if the one thing that you come out from this talk is that, oh, Rosette is cool and I should check it out, I actually would be perfectly happy with that. Rosette is amazing. It's very mature. There's lots and lots of tools that are built on top of Rosette. But I think it could be even more widely used. So if you've ever reached for Z3 bindings, I would encourage you to instead look at Rosette and see if it can help you out. But we're going to build critically on top of Rosette. So let me explain how Rosette executes a program. So Rosette augments Racket with a first-class notion of symbolic variables. So the first two lines here are defining two symbolic Booleans, which means they could either be true or false. We're going to leave it unspecified. And then the rest of the program can be basically a regular Racket program. So I have conditionals. So I'm saying if x0, 2, 3, and then similarly with y1. And then I'm going to add them together as if it's regular numbers. OK, so how do I want to execute this program? So I'm going to go line by line. So the first one is going to create a binding for x0. And on the right-hand side, we have this thing called a symbolic union, which is basically a list of pairs, where the first component of the pair is a guard, and the second component of the pair is a concrete value. So on the left-hand side, we have a formula, and that's a logical variable, x sub 0. And on the right-hand side, we have any kind of Racket value. So here, in this case, these are concrete Racket Booleans, true and false. OK, so I can do the exact same thing with x1 and get a very, very similar structure. And then what happens when I try to evaluate the right-hand side of the binding for y0? I have a conditional. And the conditional is going to be on this symbolic union, which could be either true and false. So what's going to happen is, like in traditional symbolic execution, we're going to have to explore both paths. So we're going to evaluate the true branch and the false branch. And then what's going to happen is we're going to merge those results together in order to get another symbolic union. Okay? So the binding for y0 is going to be this symbolic union, where we have the concrete values 2 and 3, which are guarded by those same logic variables. And very similarly for y1, we'll do the same. Okay, so then what happens when we get to some primitive operation like plus? Well, we're going to add the y0 and the y1 together. These things are symbolic quantities. They're symbolic unions, though, so we can't just apply addition ordinarily to them. So what Roulette also does is it lifts the operations of the language to work also over these symbolic unions. And in this case, what we can do is essentially take the Cartesian products, apply the primitive, the real addition to it, and then merge together those results into another symbolic union. So it looks like this much larger symbolic union here, and we have some of the Boolean formula. And you'll notice that we have a little bit of savings here because there's actually 2 ways to add up to 6. So we have a Boolean formula that's a little larger for that particular result. Okay, so in terms of symbolic execution, what is this really telling us? This is telling us all of the ways that you can get these results. So the left-hand side of symbolic union, the formulas, every model of that formula corresponds to some concrete execution where you've instantiated the x0 or x1 with some choice of a Boolean. So for the model x0 and x1, where we have assignments true and true, that leads to 2 and 3, which gives you 5. So if we go through the symbolic union and we look at all of the models, that summarizes all the possible concrete executions of the program. So we can do the same thing with 7. And then for 6, there's 2 ways to get 6. And we can see that reflected in the fact that the Boolean formula, the guard, has 2 models, where we have false and true and true and false. Okay? So 2 of the main ideas of symbolic evaluation, and I've given a pretty simplified look with respect to that. There's a lot more ideas, so you can look at the Roulette paper for more of the details. But I think the 2 main ideas are when you get to a conditional, you're going to execute both branches, and then you're going to merge the results into symbolic unions. And the second idea is then you lift operations of the language to work over those quantities. So let me compare this a little bit with some other techniques that you might be familiar with. So symbolic evaluation in lots of cases is able to avoid path explosion via this merging. So this is similar to in bounded model checking where there's a merging that occurs to avoid path explosion. And then symbolic evaluation also avoids having to encode every single language construct that you have in terms of a formula. This is similar to symbolic execution. So you can inherit the semantics of the programming language instead of having to encode everything manually into some formula or symbolic representation. So in some sense, you can think of symbolic evaluation a la Roulette as combining the best of bounded model checking and symbolic execution. It's a kind of a hybrid of the 2. Okay, so that's about symbolic evaluation. What has that got to do with inference? Well, I'm going to have basically the same program, and you can think of it almost the exact same way, except think of the symbolic variables being generated instead as now random variables. So instead of define symbolic, we're just going to have flips. And you can think of running and evaluating this in exactly the same way. The only difference is going to be there's probabilities associated with these logic variables. So I'm going to run through each of the lines again, and it's going to be exactly the same other than we're keeping track of probabilities. So the first one here is we have the same symbolic union as we have before, but then we have this W here, which is a weight map associating logic variables with their probability. So this is a global map that we're just going to keep track of, where here x0 is mapping to 0.4. And the same thing on the next line, except now we're updating this weight map to also have a mapping for x1, which is 0.7. And then we have the exact same symbolic union as we had before. Okay, so you can think of evaluating the program Roulette style, except now we're going to keep track of this weight map. And now I have to do something with that weight map. And now this is where inference via knowledge compilation comes in. And as was mentioned before, a lot of the inspiration comes from the DICE programming language, but there's also some prior work that is inspired this work as well. Okay, so how are we actually going to calculate the probabilities of the various results that we get at the end? And what we're going to do is we're going to do weighted model counting. So like I said before, every model of these guards corresponds to a concrete execution trace. Now what we're going to do is we're just going to weight each of those traces and then add them up. So in the first example, we have x0 and x1. And if we look at that weight map, well, we can calculate the probability of that particular concrete execution by just multiplying those two together. And we get the probability that 5 occurs. And very much similarly for 7, except now we're going to take 1 minus the probability associated with the logic variables. And then for 6, there's 2 models, and therefore we're going to take the weights of both of those traces and then add them together to get the result for 6. But we said, efficiency is really important, so how are we actually going to calculate these weighted model counts? Knowledge compilation. So these guards are going to be represented by binary decision diagrams, and then binary decision diagrams admit an efficient weighted model counting algorithm. Now, you can't always, perhaps, efficiently compile to a BDD, but if you can get there, then you can do the weighted model counting very efficiently. OK, so then the final result is this probability distribution at the end. So you get your symbolic union, you calculate the weighted model counts from the BDDs, and then that gives you your answer. OK, so the main idea is to compile these Boolean formulas into BDDs and then perform the weighted model counting. But you have to use that auxiliary weight map in order to actually do that operation. And so what are the consequences of doing so? Well, the knowledge compilation bit gives you scalable inference for discrete PPLs. And then when you add that to symbolic evaluation, then you also get expressivity as a result, because the symbolic evaluator is doing the very hard work of converting a program with a lot of high-level language features into the summary of all possible executions, which you can then do the weighted model counts on efficiently. OK, so how expressive is expressive? I gave you the example in the beginning, but just to drive the point home, I implemented this slideshow in #lang roulette. So that demo that you saw earlier where I was interacting with the error rate was actually running the roulette program. So you can see here, this is the language implementation that I talked about earlier. This is memory perturbing operations. And then here's the program that I was running. And then here's the GUI that actually renders that and performs the inference. And what's interesting here is that Rosette has interoperation with the host language Racket. So since Racket has slideshow capabilities, then we're able to just require in Racket slideshow capabilities and then just use the flip capability for the example. OK, so if it's expressive enough to write your PLDI slides, then it's pretty expressive, I think. OK, so I mentioned we're interested in the intersection of these things. So we think roulette is a good answer to that question of what exists in that space, with a few obvious caveats, which I will now go into. And there's perhaps more. You can see the paper for more caveats. But the two perhaps most important ones is that we're talking about discrete probability here and not continuous probability. So there's potentially some interesting work combining symbolic evaluation and being able to do continuous random variables. But at the moment, roulette does not support that. And the other thing is that it's unclear from the current design naively how to accommodate some features like almost sure termination. So there are some limitations with naive symbolic evaluation, but combining it with other techniques, say, for example, laziness, you might be able to overcome some of these. So these are things for future work. Let me say a little bit about what else is in the paper. So we have 2 theoretical developments. One is a model of an idealized version of Rosette, which extends on existing work on the theory of Rosette. And in particular, extending it to handle things like mutation, which is important for, say, conditioning. That theoretical development is set up in a way which nicely generalizes to Roulette and the correctness of Roulette. So everything in the Rosette setting has a nice analog in the Roulette setting to nicely generalize. So Jack and John did a lot of work getting that, so thank you. The other thing is we have some benchmarks comparing Roulette to dice, and we see that it's relatively competitive with dice on most of the benchmarks. So the summary is really that you get a lot of additional expressivity, but you're not actually losing performance from that. And there's lots more fun stuff, so I encourage you to check that out if you're interested. The other thing that I'll say is, at least for me personally, I'm really interested in people trying this out and telling us about their experience and if they have ideas or applications. So I've tried to make it as easy to get as possible. So if you have Racket installed on your computer, there's a single command that you run in Bash that will get Roulette and will get it running, I think. And there's also documentation online that covers the whole language that we've implemented so far. So please, if you're interested and have applications, try it out and come talk to Jack and me later if you're interested. Thanks.
Thanks for that great talk, Cameron.
Let's take one question before lunch. I have, go ahead, Frost.
For the nice talk. So from the expressive standpoint, it seems the large gains in expressiveness in Roulette are from more PL features, data structures, all that stuff, modules. But in terms of the statistical modeling, it's restricted to sort of these discrete distributions over a finite number of variables. Have you found cases where this increase of the sort of PL expressiveness enables you to write models which are finite and discrete, but other systems, you know, in principle they should be able to, but it's just far too complicated or they're not ergonomic enough? And what are some examples of that?
Yeah, so that's a great question. I would say that one of the things is that you can develop much more quickly when you have a more expressive host language. So one of the examples that we have in the paper is we were able to take an existing implementation of a logic programming language in Scheme and just directly embed it in a Roulette program and have a probabilistic logic programming language out of that, albeit one that's very inefficient in certain ways. So I think from my perspective, having increased expressiveness just in the PL side of things and not perhaps in other features will allow you to write programs much more quickly and easily. And I think that's good for developers, hopefully.
Great. Okay, well, let's thank Cameron again and all of our speakers. Thanks for coming to the session. And now it's lunch.
1, 1, 1, 1, 1.
All right, folks, welcome back from lunch. Hope you enjoyed the food. My name is Pavel Pinchaha. I'm a professor at the University of Utah, and we're going to be kicking off here our session on numerics. Really exciting to have a numeric session at PLDI. It's growing in importance, and there's a lot of very cool work applying formal methods thinking, applying programming languages techniques to numerics, and we're going to have a lot of that highlighted today in the program. So the first talk is going to be by Qian Chen, and she's going to be talking about using traditional optimization techniques to solve floating point constraints. So, Qian, please.
Yeah, thank you. Hello, everyone. I'm Qian Chen from Nanjing University. Today, I'm going to talk about our work, solving floating point constraints with continuous optimization. Pure floating point constraint solvers are useful when verifying programs that perform exclusively floating point computations, such as numerical libraries or scientific and high-performance computing benchmarks. Existing solution methods primarily rely on SMT solvers. They integrate an SAT solver for handling the propositional structure of constraints alongside a specialized series solver. Despite their ability to cope with logical constraints across various series, their solving in the theory of floating point arithmetic remains a significant challenge. Along with disadvantages, for example, when the constraint is complex, they will generate large SAT problems, which are difficult to solve efficiently. Recently, a separate line of work emerged approaching the problem from a new perspective. Specifically, it leverages mathematical optimization methods to find solutions to satisfiable floating point constraints. Take a work called xset as an example. The key idea of xset is to reduce the original constraint pi into a mathematical function r, such that finding values of x to satisfy pi is equivalent to finding values of x to achieve the global minimum of r. And they employ Monte Carlo Markov chain to solve the mathematical functions. xset has proven to be both effective and efficient, outperforming existing SMT solvers like these three by a large margin. Despite the great success achieved by xset, there remains plenty of room for improvement, including its translation rules and the mathematical optimization method, MCMC. MCMC relies on random sampling to explore the search space, resulting in lots of iterations to effectively sample from the entire space, and eventually leads to slow convergence to the target distribution. Driven by the shortcomings of xset, we propose a new MO-based method. Our insight is that over the past decade, gradient descent has shown extraordinary capabilities in tackling complex optimization problems. For example, in deep learning, gradient descent is often used to minimize loss functions whose parameter size can scale to trillions. Thus, we want to employ gradient descent as the underlying MO method for solving the mathematical functions corresponding to the original constraints. This requires that the mathematical functions are continuously differentiable, so we design the translation rules to translate the floating point constraints into continuous mathematical functions. At the same time, we further simplify the generated functions to reduce the complexity of the function for the overall constraint. And evidence show that the reduced complexity often improves the performance of MO method. Okay, now I'm going to use a constraint from SMT Computation 2024 to present the high-level workflow of our approach, so that everyone can get an intuitive impression of our method. Step 1, we construct an objective function from the given constraint according to the translation rules that we design. The rules will be further introduced later. For the first clause, A is less than or equal to B. Its objective function is presented in equation 1. We note that the function attains its global minimum, that is to say 0, only if the clause A is less than or equal to B holds. Otherwise, the function returns a positive number, indicating the clause has not been satisfied. For the second to the last clause, their objective functions are presented in equation 2 to 7, and the objective function for the entire constraint based on those individual functions for each clause is shown in equation 8. It requires the 7th clause to be satisfied at the same time when the entire constraint is satisfied. The capital F returns 0 if and only if all 7 individual functions evaluate to 0. Conversely, if any individual clause does not hold, its corresponding objective function returns a positive number, and consequently, the overall objective function f also returns a positive number. Step 2 is to solve the objective function, that is, to solve equation 8 for values of a, b, c, d, e, f, such that they can achieve the global minimum of f and thus satisfy the original constraint. Specifically, in this step, for each starting point, gradient descent first looks for a new set of values for all variables. For this example, after 2 iterations, gradient descent finds values that reach the global minimum. Then we validate the solution. First, we check whether the gradient of f at the current values of a to f is 0. If not, these values cannot attain the global minimum of f. Second, when the gradient is 0, we examine whether the value of f equals 0 under the current set values of a to f. If not, these values cannot be a model of the constraint. Third, when both gradient and the value of f is 0, we apply the current values of a to f to the original constraint to verify its correctness. Next, I'll give a detailed presentation of our MO-based solving methodology. As mentioned earlier, the key to a MO-based approach is to make the minimum value of the corresponding objective function correspond to the solution to the constraints. For this reason, the first rule when designing our objective function is to regard it as a metric for measuring how far the current set of value is from becoming a model of pi. The closer input values are to becoming a model, the smaller the value of objective function is. Secondly, we want the generated objective functions to be continuous and simple at the same time. So the gradient descent method can be applied to underlying solving, and the complexity of the problem can be reduced. Firstly, for operations equal, less than or equal to, greater than or equal to, we define translation rules that generate exclusively piecewise linear objective functions. For less than and equal and greater than, we follow the intuition for less than or equal to and greater than or equal to. Specifically, we treat the strict inequality A is greater than B as a non-strict inequality A is greater than or equal to B plus epsilon. The epsilon is the minimum positive subnormal number according to IEEE 754 standard. The two inequalities are equivalent according to floating point semantics, and after such conversion, we can simply apply the translation rules for greater than or equal to derive that for greater than, to avoid possible errors caused by the finite precision of floating point representation. We shift the term, and the final translation rule for A is greater than B is to non-strictly compare A minus B and epsilon. For not equal, we use aforementioned rules for combination. For disjunction and conjunction of two constraints, we use multiplication and addition respectively to ensure that only one of the two constraints needs to be satisfied or both need to be satisfied. At the same time, since the first 5 rules we design are linear, the complexity of objective functions generated by subsequent combinations will also be alleviated. Now let's go through the translation procedure quickly. First, we represent the constraints as a parse tree and then use DFS to traverse it. Our solving procedure mainly consists of 4 components. We employ gradient descent with randomly selected starting points to solve the objective function. And when gradient descent returns a solution, we check its validity. It is necessary to check the validity of returned solutions due to some floating point intricacies. Only with the validation procedure can ensure the soundness of our approach. Now I will go through our validation process in detail. We first verify whether or not the gradient of the objective function exists. If not, we determine by returning we determinate by returning the current solution or unknown, depending on whether the current values satisfy the constraint or not. On the other hand, if the gradient exists, we perform a three-step validation mentioned before. First, we check if the gradient is 0. If it is not, the solution cannot be a global minimum of the objective function. Second, if gradient is 0, we check whether Rx attains 0. If not, x cannot be a model of the constraint. Third, when both gradient and function value are 0, we check whether x is a model of pi. This validation process not only ensures the soundness of our approach, but also improves the overall efficiency. We implement our method into a solver called Grader and select 6 other solvers to compare with, including MO-based solvers, fuzzing-based solver, and classic SMT solvers. And we use 2 benchmarks for evaluation, with our own benchmark focusing more on challenging floating point constraints. The first table shows the results of all evaluated solvers on JFS benchmarks. The right-hand side figure plots the time of each solver on each constraint. We can see that in terms of the time, the number of constraints solved, Grader, BitVuzla, and CVC5 ranks among the top. However, Grader demonstrates a higher efficiency than BitVuzla and CVC5. Compared to XSET and CoverMe, Grader is more effective and efficient. When exclude constraints that Grader can solve while XSET or CoverMe cannot, the advantage of Grader in solving time will be more obvious. Finally, JFS and D3 are the least effective baselines, solving significantly fewer constraints but running much slower compared to Grader. Now we come to the results on our own benchmarks. This time, although the number of solved constraints for Grader is the same as that of BitVuzla and CVC5, the time it takes is much less, and Grader is also faster than all other solvers. To conclude, we introduce Grader, a mathematical optimization-based floating point constraint solver, and the main advantages of Grader over existing MO-based solver lie in the simplicity and the continuity of our translation rules and the effectiveness of a gradient-based MO method. And that's all for my talk. Thank you.
All right, so we're going to do questions. And do you want me to run it? Sure. Question?
Hi, I'm from State University of New York, South Korea. I'm the author of the XSAT that you just cited. And I'm very surprised that this paper have very mixed feelings because I do not understand the delta between this work and the XSAT work. If I understand correctly, the most biggest difference is that you use a different mathematical optimization backend. That is a gradient-based backend. And the original XSAT paper that it was using MCMC. A second question is, I'm also the, okay.
So the difference between the two work lies in 2 parts, as I stated here. The gradient-based method is inside of our whole work, and in order to use the gradient descent, we design more simple and continuous translation rules so that the underlying method can be applied.
Okay. I'm going to try to make sure we can get many questions, but I will note that there's a more detailed ablation study in the paper. Are there other people who want to ask a question?
Hi, Jalen from Yale University. Great technique. I just want to, could you go back to page 11 really quickly? I have a question regarding that.
Okay.
Nothing too big. I was just wondering, how did you pick the epsilon? Do you pick epsilon based on the size of A and B? Or
It's
just a small value?
it is a set.
Small is possible to normalize value, I would assume. Okay. Yeah. Okay. Well, one just quick note is it might be the case where, because epsilon is so small, like b minus a plus epsilon, the epsilon might disappear due to rounding error. So maybe it might be something you might want to look into. I don't know.
Sorry, I don't understand.
Oh, I see. We can talk later.
Oh, okay,
Great.
okay.
Yeah. Yeah, often better to go into detail offline. Other questions? There was one in the back. I'll take an opportunity to ask a question. So I assume the results depend on the initial value chosen.
And actually, for solvers that depend on the randomly generated starting point, we run each solver on each constraint like 10 times. So the impact of the starting points we think can be ignored.
Do you think it would be useful to use one of these machine learning frameworks like PyTorch to test many more initial conditions in parallel?
Well, maybe.
Okay. Let's give our speaker another round of applause. Thank you, Chen. And let's have our next speaker set up. I will quiet this. Really exciting entry in this line of work on verified deep neural networks, the ability to verify these much larger computations accurately. So I'm really excited about this talk that Li Jiaying will be presenting on support triangle machines. Jiaying, please take it away.
Okay, thank you everyone, and thank you for the introducing. Welcome to my talk. And today my talk is about our latest work, which is named Support Triangle Machine. Actually, when people first hear about this title or saw this title, they just thought of what the hell is that? Is there any relationship with the support vector machine? But from my point of view, there's no connection with the SVM. And support triangle machine is just an approximation lifting technique that can be used in the formal verification. I will show you now. So in this talk, I will first cover the background and then present our goals and our works. And after that, I will present the problem formulation. And the next is our main part, support triangle machine details. And before closing this talk, I will show some evaluation results that can help you to gain some confidence in our technique. So first, the background, the formal verification of deep neural networks. So I think, as you know, that in the last decades, the deep neural networks has been increasingly popular due to their exceptional performance in many challenging tasks. But researchers also found that deep neural networks can subject to security concerns. This is a typical example from a well-known paper, and as a result, before deploying deep neural networks into a real scenario, they must be formally verified. There are roughly two kinds of method, exact method and approximate method. Exact methods are really precise. They are based on SMT solving or linear programming or abstract. And the problem with the exact method is they are inefficient, and they cannot scalable to non-toy neural networks. And for the approximate method, they are based on the approximation or the methodology called abstract interpretation. And one of the main challenges in the approximate method is how can the nonlinear activation functions are handled. So based on the way they handle the nonlinear functions, they can be classified into single neuron approximation method and a multi-neuron approximation method. And in single neuron approximation method, they just ignore the relationship between different neurons. So they only consider one input neuron for at one time for the activation function. As a result, the input-output pair just stays in the 2D space, and only the planar geometry needs to be considered. As a result, these methods are usually simple, straightforward, but the result is less precise. And in comparison, multi-neuron approximate method, they try to consider the relationship between different input neurons. And indeed, they consider a group of input neurons, and thus the input-output pair are in the 2ND space, and where the high-dimensional geometry must be considered. As a result, the result of multi-neuron approximate method are more precise, but their design and development are very complicated and error-prone. So the red figure just shows some examples. So our goal is try to make the multi-neuron approximation construction much simpler and much easier. So so up to now we have published 2 papers. The first one in Propo 24. It is called Reductive approximation, and it tries to approximate the convex over Reductive functions by assembling selective faces of the convex hull in the high-dimensional space. And the other one is the paper I present here. It's called Super Triangular Machine. It tries to bridge the gap between the single neuron approximation method and the multi-neuron approximation method. And the idea is just to do the approximation lifting. I'll show you how it works. And before that, I will formulate the problem. So here's a simple problem formulation. We call it convex approximation lifting. It takes a triple as the input, where the S here donate to the single neuron approximation, and it try to derive the M, the multi-neuron approximation, and the other 2 inputs are the X, which donate to the input convex set, and F is the exact transformation. So for example, in the neural networks, F can be the Reductive function, the sigmoid function, or the hypertangent. Yeah, that's it. And we use a technique, we call it HP pairing technique. It's short for the hyperplane point pairing. It says that an n plus 1 dimensional hyperplane can be determined by an n dimensional hyperplane and a point of it. It is very abstract. So for example, when n equal to 0, that means a line can be determined by 2 points, 2 distinct points. And when n equal to 1, that means a plane can be determined by a line and a point out of that line. And in the high dimensional space, the property also holds. And in Propo 24, we have applied the technique to do the Reductive approximation. The idea is very simple. We just need to track how its vertices and hyperplanes are transformed using the Reductive function. And after that, So for example, here the vertices A, after the value transformation, it become A prime. And this edge, DE, after the value transformation, it become D prime, E prime. And after that, we can assemble one hyperplane here. Just take A prime, D prime, E prime. That is, so the idea is simple, but the implementation can be a little more complex. Yeah. And after that, we found that the HP pairing technique might be more powerful than that. It can go beyond the value hole approximation. And actually, we have two observations. The first one is we can use that technique to construct multi-neural approximation for any contiguous and a two piecewise linear function. This is very straightforward. And how about other type of functions? We can also do that. I will show you later. And the other observation is that we can even use the technique to construct the single neural approximation. This is seems trivial, but this is a very important observation. Because it indicates that the technique might provide us a unified way to construct the approximation construction for both multi-neural setting and the single neural setting. And it also suggests that there might be some relationship between the single neuron approximation and the multi-neural approximation. And it's to inspire us to explore further, and it also makes our STM is possible. So in essence, the HP pairing technique that can link the single neuron approximation and multi-neuron approximation through a structure, through the triangle structure. That is the key. And for the triangle, the two sides here, just provides the transformation for the hyperplanes and the vertices. And the other side just donates the boundary of the approximation. And it shows us how we should pair the hyperplane and the vertices. And one naive question, what if we do not have the triangle? We can create one. For example, here, suppose this is the F, and this is the over approximation. We can create a triangle here. Then we can apply the same technique. So here's a formal definition of this support triangle. And we call it a support triangle because it is a triangle and it supports the boundary of the approximation. And we have distilled the triangle lifting technique just from the PLDI 24, how the value hole approximation is made. And that's it. And another property that is really, really interesting is the compositionality, which is very beautiful in the computer science, I think. And we found that for the single neural approximation, we can decompose them very easily based on the following rules. So for the single neural approximation, we can first split it into two parts, the upper part and the lower part. For example, here, suppose this is the function f, and this is the single neural approximation. So we first split it into two parts, the upper part and the lower part. And for each part, we can decompose them into several linear parts. For example, for the upper approximation, we can split it into two parts, the first part, the second part. And each linear part can be lifted independently. And the next is, after lifting, we can compose the final approximation by just conjoin them together. This is a very important property, and proving them can take time. It's in the paper. If you are interested, you can look. You can refer to our paper. Yeah. So with all above, here's the overall algorithm for the STM. It is an iterative algorithm. It processes each output coordinate incrementally. And for each output coordinate, it decomposes the single neural approximation into linear parts and lift each linear part independently and conjoin the lifted approximation together. Yeah, and then with this approximation, it can go to the next round to process next output coordinate. And there's also one issue we haven't visited yet. What if there are multiple support triangles? And actually, there are usually an infinite number of support triangles. Which triangle should we select? Optimally, we would like to have the one that leading to the largest precision gain, but the subspace is pretty huge. It needs to consider the X and F, and also the S. So we propose a heuristic here. We just choose the triangle with the largest area. That's it. So here's our evaluation. We have evaluated 5 typical functions: linear rule, sigmoid, hypertangent, exponential, square. And we checked 2 types of single neural approximation, boxes and polyhedron. And we evaluated based on the precision, efficiency, and output complexity. And we try to evaluate the effective of our heuristics, and we try to check the performance on CL problem and DNN verification tasks. As I'm not a guy who are good at the experimental experiments, I just show you some results, and I won't go to very details. So for the triangle selection heuristics, the result just so that our heuristics usually cannot find the optimal solution, but the precision loss is still very small. And on the CL problem, CM is sort of for the convex approximation lifting, and we have so many settings, and the result so that our method is more precise than the Cartesian product, but less precise than the convex whole computation, but it's more efficient. And for the sigmoid and the hypertangent, we also compare with the state-of-art method, the Prima. The result there. And the last one is on the DNA verification task. We have trained several neural networks with the linear rule activation functions, with the sigmoid and hypertangent activation functions. And the conclusion is that our method is more precise than the single neural approximation method, and it can achieve the same level of precision with the state-of-art multi-neural approximation method, and it is more efficient than that. That's it. Yeah. So in this work, we try to bridge the gap between single neural approximation method and the multi-neural approximation method through lifting. And we formulated it as a novel problem, convex approximation lifting. And we invent the support triangle structure and derive a triangle lifting technique. And we introduce the STM to solve the L problem. And we do some preliminary evaluations. That's it. Any questions?
Yep. All right. Are there questions for Jiaying? I will start with a question. If we have techniques like this, what does this tell us about the design of the activation functions themselves? Right? Does it make sense to design activation functions that are better approximated in this multi-neuron setting?
So your question is about does this approach can tell us some lesson on designing activation function?
That's right.
This is a really good question, I think. But I think in the community, usually we cannot control the design of the activation function, right? Usually the AI guys can come up with some ideas, and we need to handle handle these functions. But from my point of view, if we can have some control, we would like to have the function as simple as possible, I think. Yeah.
That's a funny but realistic answer. Yes. Other questions about this technique?
Yeah, thanks a lot for the great talk. I have a question about that. Yeah, I'm Jenya from Kyushu University. So I have a question that, so at the beginning you said that the existing approaches about using the multi-neuron approximation is hard and it's difficult. So it's complicated. I wonder, what do you mean concretely, like the computational complexity or the efforts that are taken by the developers?
Okay. So the question is about what I've said is that multi-neural approximations are complicated error-prone. What does the complicated means? It is it can be referred to the complexity, but what I said is the design and the development of this method is really complicated, really difficult. Yeah.
I have another question for you.
Yeah.
Have you considered using these approximation techniques, outside deep neural network verification? I could imagine potentially using this in like collision detection and graphics or something like that. Do you have other applications in mind?
So the question is about are there any possibilities we can apply the same technique to other domains? For the domains you mentioned, frankly speaking, we haven't considered that yet, but we have considered some other things in the software verification. I think both the HP pairing technique and also the decomposition is very general. I think it should be promising to apply the same technique or just modify some part to be used in the software verification. That is my thought.
Okay, very cool. Please give Chang a round of applause again.
Thank you.
All right. So our next speaker, Se-hyuk, is going to give us an update on this very exciting long-running project of building correctly rounded math libraries. And there's some exciting improvements to how you can do that in a way that's independent of the rounding mode that the application is actually using. So we're going to give him a second to set up, and then we'll get right into that.
We also want to test some laser pointers, see if they work.
Oh, okay. Cool.
The laser pointers work?
Yeah, this works.
Yes, okay. The microphone?
What do I need to press?
Okay, so again, Se-hyuk Park of Rutgers on correctly rounded math libraries that are rounding mode independent. Please.
Hello everyone, I'm here on behalf of the Rutgers Architecture and Programming Languages Lab to present our work on our RLBEM project. The overarching goal of RLBEM is to improve the portability of scientific computing. Scientific computing makes extensive use of math libraries, and for applications to be portable, the math libraries they use should ideally produce correct standardized results. And for this purpose, RLBM believes there needs to be correctly rounded math libraries. So I'll start off by explaining what correctly rounded math libraries are. Given a function and an input, the correctly rounded result is the output of the function evaluated in infinite precision, directly rounded to some target format using some rounding rule. So here's an example. Suppose v1 through v3 represent 3 consecutive 32-bit floats. And let's say for a given input x1, the log value evaluated in infinite precision is this value shown here. For the vast majority of their inputs, elementary functions like log produce irrational values that are not exactly representable in finite precision. In such cases, the real function result would need to be rounded. Under round to nearest, log of x1 would round to its nearest 32-bit float, and that would make v2 the correctly rounded result. A function that can produce correctly rounded results for all its inputs is a correctly rounded function. A math library consisting of such functions is a correctly rounded math library, and RLBM believes that that is the gold standard for reproducible numerical programming. Now, math libraries generally approximate elementary functions like log using polynomials. The most conventional approach to developing correctly rounded elementary functions is the minimax approach, which minimizes overall inputs the maximum error incurred by a polynomial relative to the real function results. In contrast, instead of approximating the real function results, RLBM proposes directly approximating the correctly rounded results. Given a function, each correctly rounded result in some final target representation, like 32-bit floats, is going to have a range of values in some intermediate representation with higher precision, like 64-bit doubles, that all round to the correctly rounded result. Such ranges are referred to as rounding intervals. Now, relative to the real function result, the size of a rounding interval is 1 up, or unit of least precision. You can think of the up for any real number as the distance between the two nearest neighboring floating point numbers. So in this example, the up of log of x1 would be the distance between v1 and v2. The key takeaway here is that an approximation can incur up to 1 up of error relative to the real function result and still produce the correctly rounded result so long as its output is within this rounding interval. Now, given this 1 up leeway, rounding intervals offer a large degree of freedom of tolerable error as it pertains to correct rounding. This large degree of freedom allows for approximation using low-degree polynomials with low evaluation overheads. Now, to utilize such rounding intervals, we need to have correctly rounded results to begin with. Fortunately, there exist math libraries like MPFR that can produce correctly rounded results for any arbitrary target representation. The negative is that the functions in such libraries can be a bit too slow to be used directly in programs, but nevertheless, they are suitable for math library development. Using the correctly rounded results provided by such libraries as oracles, RLBM identifies a more optimized approximation of those results using the associated rounding intervals. So in short, RLBM's motto is, give us your results, and we'll find an efficient way of reproducing them. So here's an overview of the steps that RLBM takes towards accomplishing this goal. So as alluded to earlier, RLBM starts off with the correctly rounded oracle results for a given function and the associated rounding intervals. I mentioned earlier that as long as its outputs are within these intervals, a polynomial can produce correctly rounded results. So the bounds on these intervals can be thought of as linear constraints on the expected outputs. RLBM encodes these constraints into a system of linear inequalities, and in doing so, it transforms polynomial generation into a linear programming problem. It then uses an LP solver to identify the appropriate coefficients that allow the final polynomial to produce values within the target rounding intervals. So this explains how RLBM produces correctly rounded results for a single representation. Given the variety of floating point formats that exist, it would be ideal to have for each function a single implementation that can produce correctly rounded results for multiple representations. And for this purpose, RLBM employs a non-standard rounding mode known as round to odd. Specifically, RLBM has observed that the correctly rounded n plus 2-bit result under round to odd is guaranteed to round to the correctly rounded result for any representation with up to n bits. By utilizing this observation, RLBM has become the first math library that provides for each function that it supports a single implementation that can produce correctly rounded results for all representations with up to 32 bits and for all standard rounding modes. For those of you who are interested in more details behind this technique, I would highly recommend reading the POPL 2022 paper. Now, despite RLBM's broad applicability, the correctness of its functions comes with a caveat. So let's suppose that an application, which could be running under any standard rounding mode, wants to use the RLBM library to obtain the output of log rounded to a 32-bit float. Here are the steps it would need to take. First, it would need to save its original rounding mode. Next, it will need to switch the rounding mode to round to nearest before invoking RLBM's log function. Then, it will need to return back to the original rounding mode before obtaining the final desired result. Now, RLBM's outputs can be rounded to the correctly rounded results under any standard rounding mode, but the functions themselves need to be invoked only under round to nearest. This is because RLBM performs floating point operations during polynomial generation, and while doing so, it uses round to nearest as the default implementation rounding mode. The rounding mode switch to round to nearest is required to avoid any rounding-induced variability or any rounding behavior not observed during the polynomial generation process. But these frequent rounding mode switches are not without costs, and they incur additional latency for our final functions. To overcome RLBM's reliance on round to nearest and the associated overheads, we need to handle rounding-induced variability without explicitly setting the rounding mode. For this purpose, we have designed two new methods of developing correctly rounded functions that can be directly invoked under any application rounding mode. Our first method, rounding invariant outputs, accomplishes the goal by enforcing a single fixed implementation rounding mode within the code. Our second method, rounding invariant input bounds, accounts for rounding-induced variability during the process of generating the polynomials. So I will go over our rounding invariant outputs approach first. The goal of the rounding invariant outputs approach is to develop functions that always emulate round to zero behavior regardless of the rounding mode used by the invoking application. With respect to RLBM's functions, the primary sources of rounding-induced variability are the floating point addition and multiplication operations. To accomplish our goal of emulating round to zero, we develop custom addition and multiplication operations that always produce round to zero results. Now, to actually implement these operations, we need to address the following issues. First, we need to be able to ascertain under any rounding mode whether or not a floating point result conforms to round to zero. Now, we have affirmed that the rounding errors associated with floating point results can serve as appropriate indicators. And to utilize these errors, we employ error-free transformations, which are floating point algorithms designed to compute the rounding errors incurred by floating point operations. Secondly, given a non-round to zero floating point result, we need to know how to adjust its value accordingly. When the corresponding real arithmetic result is not exactly representable, a floating point sum or product will always return one of the two nearest neighboring floating point numbers. I mentioned earlier in the talk that the distance between two such numbers is 1 up. By definition, round to zero should always return the floating point neighbor with the smaller magnitude. Therefore, given a non-round to zero result, we can subtract 1 up from its magnitude to adjust its value in accordance with round to zero. So here is an illustration of how we apply these ideas in the context of our addition operation. So let's suppose one of our functions performs addition using the operand shown on the slide. Given these two operands, the real arithmetic result will not be exactly representable in double precision. Assuming that the current rounding mode is round up, a plus b will return the immediate floating point successor, and that number is represented by the value SOG on the bottom right. The value we want under round to zero, on the other hand, is the immediate floating point predecessor, and that number is represented by the value SRZ on the bottom left. So the task at hand here is to derive SRZ from SOG without any direct access to the real arithmetic sum or any explicit information about the current rounding mode. Now, floating point sums can differ across different rounding modes if and only if the real arithmetic result is not exactly representable. In such cases, a plus b would have incurred some amount of rounding error. To confirm the presence of this error, we apply two instructions that collectively compute a floating point approximation of the rounding error incurred by a plus b. Now, we prove in our paper that our error approximation t is non-zero if and only if rounding error exists in the initial floating point sum s. We also prove that when such is the case, the sign of t differs from that of s if and only if s has a magnitude greater than its real arithmetic counterpart. When both these conditions hold, we can conclude that the original floating point sum does not conform to round to zero, and we can subtract 1 up from its magnitude to adjust its value as intended. For our multiplication operation, we use error-free transformations to similar effects to utilize the rounding error incurred by floating point multiplication. Due to time constraints, I won't be able to go into our multiplication operation, but the algorithm and the associated proofs can be found in our paper. By replacing all the additions and multiplications in our polynomials with our new custom operations, we can ensure that our functions produce correct results regardless of the rounding modes used by the invoking applications. However, to apply this method, we need to augment each and every addition and multiplication with extra instructions that reason about the associated rounding errors. And these extra instructions entail additional overheads for our code. So given these overheads, it would be ideal to handle rounding-induced variability not within the code, but during code development. And this thought brings us to our second method, rounding invariant input bounds. Given an input and a polynomial, the goal of the rounding invariant input bounds method is to bound the full range of possible outputs obtainable across different rounding modes. Now, a floating point polynomial is essentially a sequence of floating point additions and multiplications. When evaluating polynomials, our original library assumed that all instances of rounding are round to nearest. For a rounding invariant outputs approach, we fixed the rounding modes to be round to 0. For a rounding invariant input bounds approach, we lift that assumption of uniform rounding and instead assume that each operation can be performed with a separate rounding mode. Now let's take as an example the following polynomial to be evaluated over the following input. And I'd like to quickly mention that the encircled multiplication and addition symbols represent floating point operations. So in the case that multiplication and addition are performed under round down, you would obtain the final output as shown on the slide. Now when these operations are performed under round up, you would obtain a different value. Given this variability due to rounding, the rounding invariant input bounds method represents polynomial outputs not as singular values, but rather as intervals. Now with this in mind, we should note that polynomial outputs can be defined recursively. For example, the output of a polynomial p is either a constant or the sum or product of the outputs of two intermediate polynomials, p1 and p2. With the assumption of uniform rounding removed, the intermediate polynomial outputs are also rounding mode dependent. Therefore, we model not only the final outputs, but the intermediate outputs as intervals as well. Now let's suppose that the last operation performed during the evaluation of one of our polynomials is a floating point addition. Under the rounding invariant input bounds method, the objective is to identify the rounding modes and the specific instances of the operands that either minimize or maximize the final output. It is a well-known property of floating point arithmetic that floating point sums and products are bounded by the round down and round up results. Naturally, the lower and upper bounds of the final polynomial output will involve round down and round up respectively. It is also well established that floating point sums and products are monotonically non-decreasing with respect to their real arithmetic counterparts. Given two intervals, we can identify the specific values that either minimize or maximize the sum or product using the rules of interval arithmetic. Based on the rules of interval arithmetic and the properties of standard rounding modes, we prove in our paper that the bounds on the outputs of operations always involve the bounds on the operands. Now, the operand bounds are just the bounds on the outputs of some previous sequence of operations. Given our recursive definition of polynomials, we can define operand bounds recursively in the same manner. With these definitions in place, we can once again use interval arithmetic to compute the final output bounds bottom up during polynomial generation. Now, doing so would require making some changes to our pipeline. If you recall, our existing pipeline ensures correctness by confirming that a polynomial's outputs are within the target rounding intervals. Under our new approach, we need to confirm the same property for both the lower and upper bounds of output intervals. Naturally, our candidate polynomials will be subject to a tighter set of constraints. On the flip side, if both lower and upper output bounds satisfy their associated constraints for all inputs, we can ensure that the final polynomial can produce correctly rounded results irrespective of the rounding modes used during evaluation. In summary, our new methods explore different trade-offs. Our rounding invariant outputs approach requires augmenting our functions with extra instructions that reason about rounding errors. The primary benefit of this approach is that the existing pipeline can remain largely unchanged. The only adjustment required is setting the rounding mode to round to 0 during polynomial generation. On the other hand, the rounding invariant input bounds method requires making extensive changes to our pipeline, as polynomials are evaluated in a different manner and are subject to a tighter set of constraints. Conversely, the resulting functions do not require any extra instructions to produce correctly rounded results. So using these two new methods, we have developed new implementations of the various elementary functions provided by our original library. So we've spent a fair amount of time into developing these functions, so it would really be nice if they are correct. And as intended, all of our new functions produce correctly rounded results for all inputs. And I like to add that the correctness proclaimed on this slide is an extension of the correctness already offered by RLabM. This means that using our new methods, we have developed functions that can produce correctly rounded results for multiple representations and for all standard rounding modes, while being directly invocable under any application rounding mode. Now, at this point, we should remember that the primary motivation behind this research was the performance overheads incurred by the rounding mode switches required by our original library. So we need to confirm that our new functions achieve meaningful performance boosts as well. So here is a graph showing the performance speedup of the rounding invariant outputs functions over their existing RLM counterparts. And I like to mention that the latency of the original functions reflected in this slide contain the latency induced by the rounding mode switches. So as you can see from the bar on the far right, on average, the rounding invariant outputs functions achieve an approximate 1.5 times speedup over the original library. Now here are the results for the rounding invariant input bounds functions. On average, the rounding invariant input bounds functions achieve an approximate 2.3 times speedup. The speedup is more pronounced here because the rounding invariant input bounds functions do not require any extra instructions in the final code. Ostensibly, the rounding invariant input bounds functions perform the same set of core operations as their existing RLM counterparts. Therefore, this result provides a more accurate depiction of the full degree to which rounding mode switches degraded the performance of our original library. In closing, we have designed two new methods of developing correctly rounded functions that can be directly invoked under any application rounding mode. Our first method, rounding invariant outputs, accomplishes consistent correctness by enforcing round to zero as the implementation rounding mode within the code. Now, round to zero is an efficient rounding mode used across various domains of scientific computing, so we believe that our custom operations can be broadly applicable aside from just developing math libraries. And our second method, rounding invariant input bounds, accounts for rounding-induced variability during the polynomial generation process. The resulting functions do not require any explicit rounding mode switches or any extra operations to produce correctly rounded results. Using this method, we have been able to improve the performance of our library by over 2x. And on that note, I would like to welcome everyone to try out our library, and I thank everyone for their time and attention.
All right, questions? Ganesh in the back.
From University of Utah. Really like this line of work. First of all, for GPUs, it's not possible to switch rounding modes. So I guess this method was needed in the first place. Am I right?
Yes.
Only for CPU, okay.
Yes.
Can you please describe the cost of generating the library itself? Does it change in any way? So say, consider you want a 64-bit implementation of the library. And let's say that for the CPU part, you did it the old way, and now you have to do it the new way. Is there any cost in generating the library that one perceives?
Yes, so I mentioned earlier that our new rounding invariant input bounds approach imposes tighter set of constraints on our polynomial generator. So our polynomial generator would take some more time under this approach. For the 32-bit target, the difference in time wasn't too noticeable. But I imagine if the output was expanded to 64 bits, we may see some larger overheads.
Has this been applied to 64 bits at this point, or?
Not yet.
Oh, okay. Thank you. Yeah.
Okay, another question?
Thanks for the lovely talk. I'm Alistair Donaldson from Imperial College London. I just wanted to confirm then, could you go back to the previous slide so I can remember the names of your different approaches? It sounds like the rounding invariant input bounds method is just superior to the rounding invariant outputs method. Is that right? As in, it gives you something correctly rounded and it performs better. So the first one is definitely intellectually interesting, and you said it could be useful for other functions, but is the takeaway that this input bounds approach is just the better of the two?
So that's a great question. So in my talk, I primarily talked about polynomial approximations, but elementary function implementations do a little bit more than that. For example, as a first step, elementary functions have to perform a process known as range reduction to enable the usage of low-degree polynomials. And these range reduction steps are essentially floating point operations as well, and they're also rounding mode dependent. And to ensure that our polynomial generators have singular inputs, we need to fix the rounding modes for range reduction. And for that purpose, we need to use our custom round to zero operations. So in short, our rounding invariant input bounds method requires the rounding invariant outputs method to a certain degree as well. So one is built on top of the other.
Oh, in it, but is there another question?
There is another question.
super cool work. I'm Zach Tatlock from the University of Washington. One thing I was wondering, so you're kind of like using this error term from, two-sum, like EFT style stuff. Do you ever know anything about the order of the arguments? Like, can you use fast two-sum insights? And similarly, there's also, three-sum and other things. If you're doing the polynomial evaluation, can you use some of these larger adders, these in their error terms, to, I don't know, fuse some of the polynomial evaluation steps and get more speed up?
So with respect to the question about the arguments, so I did not explicitly label it in the slide, but we're actually using fast two-sum, so we need to ensure that one operand is greater than the other. And with regards to your question about extending it to three sums, etc., I think the broadening of the various error-free transformation techniques and applying them would require more analysis on how certain polynomial coefficients could allow for such applications, and etc. And that analysis is future work. Yeah.
Okay, let's please thank Sahyok. Right, I've learned my lesson. I'm going to avoid doing the introduction right away. I don't have one off the top of my head. Sorry, Zach. All right. So for the last talk of today's session, we have Arielle Kellison. She's Galois, previously at Cornell, and she's going to be talking to us about a very interesting piece of work looking at scalability for floating point backward error analysis by leveraging a bunch of ideas from type theory. So Arielle, please.
Thank you. All right. So this talk is about Bean, a language for backward error analysis designed and implemented by me, as well as Laura Zielinski, David Bindel, and Justin Xu. So why did we develop Bean? And I had to take a moment to think about this slide in particular because of the keynote talk this morning. What can PL do for people? I actually think that in terms of numerics, PL really has an opportunity to make a big difference in the lives of people, specifically because numerical results are often used now to inform policy decisions that affect all of us. So in particular, we have some examples here. Energy demand forecasting shapes infrastructure planning. Disease spread models inform public health responses, and we actually saw the use of this during the COVID-19 pandemic. And drought projections are essential for effective resource management and also for climate policy. So today I'm going to talk a little about how we can use PL to help us ensure that we have trustworthy numerical results in settings like this. So these forecast models and projections, they're all computationally demanding. They rely on billions, if not more, of floating point operations. But as we know, floating point math is inherently approximate. So every floating point operation, an add, a multiply, a divide, a subtract, introduces some small rounding error, potentially. And while each individual rounding error is quite small, these errors compound over billions of floating point operations, and they can grow too large. And our results, these forecast models and projections, the results of these models, can become untrustworthy. Thus, we need to be able to analyze these errors statically before we ever run these costly computations. So if you look in a numerical analysis textbook, you'll generally see two approaches to error analysis. The first approach is called forward error analysis, and it answers the simple question of how close is the computed result to the exact mathematically correct result. So in simple language, is your floating point result what you would expect? And the second approach is a little harder to state in plain language. It's slightly more complicated. The second approach is called backward error analysis, and it answers the question, how much would we need to perturb the input to an exact function so that it produces the computed result? And I'll explain this in more detail during this talk. So for our first approach, there are several existing static analysis tools that automate forward error analysis. These include DAISY, Precisa, FP Tuner, FP Tailor, and Numerical Fuzz, which we introduced at PLDI last year, as well as many others. And some of the authors for these tools, I think, are in the audience. Unfortunately, for the second approach, and this is a common approach that you would see, again, in a numerical analysis textbook. It's very important in the field of numerical analysis. For the second approach of backward error analysis, which is the topic of today's talk, there are no existing static analysis tools that automate it. So if you're a numerical analyst and you want some backward error analysis guarantee, there isn't a single tool available for you to use. And of course, this is where our contribution comes in. So Bean is the first static analysis tool for backward error analysis. It's a first-order language with numerical primitives and a linear coeffect type system designed for tracking backward error. Now, Bean has 3 important properties that we think are generally good for languages for error analysis. First, Bean is sound. That means that well-typed programs in Bean satisfy the backward error bound that the type system assigns them. We'll see some examples of soundness, sound programs in Bean momentarily. Secondly, Bean is useful. It infers automatically error bounds that match worst-case theoretical error bounds from the literature. So there are well-known backward error bounds from the literature for problems that we'll go into a little more detail on today. And Bean can infer these bounds. And finally, Bean is fast. So error-bound inference right now scales quadratically with the number of floating point operations in a program. And while this might not seem too fast, in the terms of rounding error analysis, this is quite good. All right, so to understand how Bean works, we first need to understand the concept of backward error analysis. We can consider backward error analysis for an exact map F, and its floating point approximation tilde of F. So if we know that our floating point approximation maps a point in the input space to a point y in the output space, a backward error analysis identifies another, possibly different point from x in the input space, denoted here by tilde x, that maps under our exact function back to the computed result, so back to our floating point result. And a backward error analysis not only identifies this additional point in the input space, tilde x, but it also bounds the distance between x and this new point tilde x. And we will refer to this bound here as alpha. So alpha is showing the distance between these 2 points in the input space, and that is our backward error bound. Now, a small alpha is desirable. A small backward error bound is desirable. This means that the floating point program won't magnify rounding errors. So again, on the first slide, I was saying that over billions of floating point operations, it's possible that models and simulations would magnify errors so that they become too large and we can no longer trust our results. But if we have programs with small backward error, then we know that that program is well behaved in the sense that it won't magnify our rounding errors too much. All right, so we can better understand backward error analysis with a simple example of a dot product. So in this case, the exact dot product is what we're all familiar with. It's the sum of the product of the individual components of the 2 vectors. And we can implement this in floating point arithmetic in a language like Python using a simple for loop. Now the goal of a backward error analysis is to find an alpha, our backward error bound, such that our computed floating point result equals the exact dot product over 2 perturbed vectors. These perturbed vectors are denoted by tilde u and tilde v. And these 2 perturbed vectors are within a distance of alpha of our initial inputs. So that alpha, again, is our backward error bound. It's bounding the distance between our perturbed vectors and our original inputs. Now, how we would traditionally do this by hand or in a numerical analysis textbook is we would apply a backward error model that characterizes the backward error of each of the individual floating point operations. So for example, a floating point addition is exactly equal to exact addition over some perturbed inputs that are within a distance of machine epsilon from our original inputs. Similarly, the backward error model for multiplication says that floating point multiplication equals exact multiplication over some perturbed inputs that are within half of a machine epsilon of our original inputs. So this is nice, right? It tells us what is the backward error for each individual floating point arithmetic operation, but we have many such operations in our dot product. We still don't necessarily know what alpha is. If you were to, again, look at a numerical analysis textbook, there would be several pages for describing how to compose these backward error bounds for each multiplication and each division to actually get an error bound alpha for our dot product. That's where Bean comes in handy. So we have an implementation of Bean that's based on numerical fuzz, which we introduced last year at PLDI, as well as defuzz due to Azevedo de Amorin and co-authors from 2014. All right, so this example is an implementation of dot product of two vectors u and v and r squared. So a simple example of vectors with two components in Bean. So this is our Bean program. Okay, so yes, it takes a dot product of these two vectors. Now first we deconstruct u and v, so we get the individual components of our vectors. We sequence the computations of the multiplication of these two components into the final addition. So again, this is just two vectors with two components, a simple example. And now, while this example for a Bean program shows multiplication and addition, we also, of course, have subtraction and division in our language. So we have all of the basic arithmetic operations. Now, if we run our type inference and type checker on this Bean program, it will tell us the return type of the program. So our dot product, we would expect to return a numeric type, and that's exactly what our type inference and type checker says. It says that if we evaluate this program, it will return a value of our new primitive numeric type. But our type inference also for Bean also tells us an additional piece of information, which is very important. It tells us the context that this program is well typed in. So in particular, from this type inference to the exact guarantee that we have in Bean, our backward error guarantee in Bean for this specific program says that for any vectors u and v in R squared, there exists these perturbed vectors, tilde u and tilde v, such that our Bean dot product over these initial inputs, it equals an exact dot product over these perturbed inputs, and the distance is bounded. Sorry, this isn't showing. So, whoops. And the distance between our perturbed vectors and our initial vectors is exactly what we call here this co-effect annotation that was inferred in Bean. So Bean infers these backward error bounds, and the soundness of our type system actually guarantees that all well-typed Bean programs satisfy some kind of backward error guarantee. Now, for those of you that are familiar with backward error analysis, you might be a little bit surprised here. Why should all programs satisfy a backward error guarantee? This is actually a really challenging problem because many programs that you are familiar with, such as matrix-matrix multiplication, they don't actually satisfy a backward error guarantee. So how did we design a language in which all of the programs have a backward error guarantee? And the issue at hand here is that really not all rounding errors that are introduced during the execution of a program can be interpreted as small perturbations to the input of an exact computation, and that's what we need in order to establish a backward error bound. Okay, so this is in stark contrast to forward error analysis, that first approach that I said was usually treated in the static analysis literature. Okay, so for forward error analysis, all programs have a forward error bound. So this is a really big difference, just to repeat, between forward error analysis and backward error analysis. Not all programs have a backward error bound, whereas all programs have a forward error bound. For instance, they can have a trivial forward error bound of infinity. All right, so how did we deal with this main challenge? Well, our contribution is what we call backward error lenses. Now, programs with backward error guarantees, we think, are characterized by backward error lenses. So there's really kind of been a gap, as far as we're aware, in the numerical analysis literature for characterizing kind of the set of programs that have backward error guarantees. Often there will be a backward error analysis for specific algorithms or specific programs, but really in programming languages, we're interested in defining kind of the set of programs that have a certain type of guarantee. And we believe that these types of programs are characterized by what we define as backward error lenses. All right, so a backward error lens from input space X to an output space Y is characterized by 3 transformations: a forward transformation and an approximate transformation. So we've seen these so far. The forward transformation we can think of as our exact program, computed in infinite precision. And our approximate transformation here, we can think of as our approximate or floating point transformation. But this backward map is new. This backward map is an explicit transformation that takes a point in our input space, a point X here in our input space, and a point Y in our output space. It maps both of these to another new point in our input space. That's our characteristic backward error point X tilde. Now, it's important that these maps satisfy 2 conditions that we call reconstruction and our backward error bound. And really, these 2 conditions are saying that our approximation map, this forward map here, which would represent like our floating point program, this approximation map has a backward error guarantee. So that's what those 2 conditions that our transformation, our backward error lens must satisfy, that's what those say. Now, we called these backward error lenses, kind of looking at the programming languages literature from the lenses for the view update problem from Foster and co-authors from 2007. So going all the way back to 2007, this is kind of, we renamed or rewrapped the idea of lenses into this concept of backward error lenses. All right, so we give Bean a semantics in the category of backward error lenses. And so in this category, objects are distant spaces, morphisms are backward error lenses, and then we derive our soundness guarantee that we briefly introduced earlier from the properties of these morphisms. So how well does this work in practice? So evaluation results show that Bean works well on programs with known backward error guarantees. So in our evaluation, we show that Bean infers optimal sound error bounds. So I'm hoping you all can see this table in the back, and I know it's a little bit late, so I'm going to have these little pointers to help guide us through this table. All right, so again, in our evaluation, Bean infers optimal sound error bounds on these benchmarks. 3 of these benchmarks are from linear algebra. We look at a sum, dot product, matrix vector multiplication. And 2 of these benchmarks are from polynomial evaluation. So this is a Horner's scheme and then just a traditional polynomial evaluation. All right, and these benchmarks are increasingly large input sizes. So for example, this is a sum of 50 values, 100 values, 500, 1,000, and so on and so forth. And so you can also see the increasing number of floating point operations in each of the benchmarks. And we ask the question, does the bound inferred by Bean, the backward error bound, does it match the theoretical worst case error bound from the literature? That's what we would like to know. And indeed, this blue check mark says yes. Indeed, Bean does infer optimal sound error bounds for each of these benchmarks. Okay, and that is our evidence for Bean being useful. Now, is Bean fast? Well, there's really not much to compare it to since it's the first static analysis tool of its kind. But as I said before, right now it scales quadratically with the number of floating point operations, we believe, in each of these benchmarks. And so we're going to claim that it's fast until someone can do better. I'm glad you thought that was funny. Okay, so in summary, Bean is a language for backward error analysis. You see the acronym where it came from. It's a first order language with numerical primitives and a linear coeffect type system designed for tracking backward error. It's sound, it's useful, and it's fast. And it's the first static analysis tool for backward error analysis. So you can see our paper or our GitHub repo for more information if you'd like. For example, we have a lot about language features, cool language features in the paper. So if you're like a really a PL person and you think the idea of dual context, linear, nonlinear coeffect type systems is really your jam, take a look. We also have examples for the real numerics people in the audience. We have backward error analysis of triangular linear solver using Bean, very cool. We also have implementation details, so a soundness and completeness results for the type checking algorithm. as well as additional details about our semantics. So if you're a PL semantics person, the definition of the category of backward error lenses is really neat. So take a look if you have a chance. And then just one final thing. I will be going out with one of the interns from Galois. I'm a research engineer at Galois. We are going to go and have drinks around 5 p.m. So if you see me or the intern from Galois, we will buy you a drink here in Seoul. So thanks so much for coming to my talk.
All right, we got a lot of questions.
Oh no.
Hi, thanks for the great talk and the really cool work. This is Rachit from MIT and Jane Street. Can you give some intuition of what causes a computation to not have a backward analysis map?
Yeah, so it's kind of, it's an interesting question that like doesn't have the best answer. So much in the sense that like really, if you look at the numerical analysis literature, you're going through this process, again, of just assigning backward error results to each of the individual floating point operations and trying to compose those together and seeing whether or not those rounding errors can be interpreted as perturbations to the input of an exact computation. So for example, I said matrix-matrix multiplication doesn't have a backward map, but in particular, or a backward error result, but I think what you're asking potentially is which computations cannot be embedded or interpreted inside of this backward error lens semantics. And that's a really good question that I don't know that I have an excellent answer for, to be honest, because, well, really, these types of programs sort of fail to have, they fail to satisfy one of these two conditions. And which one of those conditions they fail to satisfy is not necessarily clear to us a priori right now.
Thank you.
Yep.
Hi, thank you for a wonderful talk. I have a very specific question which arises a lot in machine learning. Floating point arithmetic is not commutative, which means if I try to do an addition operation with a bunch of floating point numbers, they may run in parallel and you may get different results.
It's not associative,
Sorry, did I say
but
commutative?
it is commutative.
Sorry, I apologize. It's not. It's not
actually
associative.
Okay.
Right?
Yes.
And this shows up all the time, and some of this is a function of the runtime behavior of how you're executing these operations in parallel versus sequential.
Mm-hmm.
So do you have any thoughts or comments about the interpretation of this language or this analysis that you're doing?
Yeah, so you're saying the static analysis actually isn't accounting for some of the runtime behavior.
That's correct, yes.
Yeah, so really what we're trying to do here is design languages and static analysis tools that emulate the type of analysis that a numerical analyst would do. So it's a very high level analysis that really isn't going down to that kind of level of granularity that you're talking about. Yeah, so that would kind of be a different research problem.
My name is Hiramishi from JJ Inc. And I once heard that, so I'm so impressed that you used lens to
that's right.
Yeah, formalize the backward error and the think of the category of the lenses. And one thing I can remember is that there is some study on automatic differentiation realized with lens and the category of such lens. Is there any relation to this?
You know, I'm not that familiar with the semantics or like using lenses in the field of autodiff, but that sounds very interesting. You know, I'm sorry, I don't know that I have necessarily anything to say about that, but it is a very interesting point. Yeah, I think lenses really appear in all of these different places. You know, in kind of like computational mathematics, they've appeared in machine learning and so on as well for semantics. And I do really think that we're not just trying to like shoehorn everything into lenses. I think that they are just kind of a very general construct that provides insight that maybe other mathematical constructs for semantics for programming languages don't necessarily do. Yeah. Yeah.
Okay, last question. Hi, I'm Bhargav from the University of Utah. So
this was a question about the error model used in the paper. It's not the 1 plus delta error model, but like it's something different. The epsilon e to the power delta like error model. So and then like we've talked a lot about backward and forward error, and they're related by a condition number. So the work we have done kind of shows that although you won't get tight bounds with just by taking condition numbers into account, you can at least try to localize the error to the specific operations that do like amplify error by a lot.
Yes.
But the problem is when like these condition numbers are closed form, but they can themselves be pretty inaccurate, and you won't get like the right amount of amplification.
Okay.
So maybe like, do you know if the e to the power delta error model has a closed form analog of condition numbers that we could use to like calculate more precise amplification factors?
That's a really interesting question. So there are only a few papers that kind of use this e to the delta rounding error model instead of the 1 plus delta rounding error model, and I think they're mostly from like the 70s. So it's it really hasn't been developed out, I think, in the way that it could be that you're describing. I think that's kind of an open area of work that I'm really hoping to see progress. Yeah.
Okay, thank you again for Ariel. Round of applause. All right, so that closes out the session on numerics. The program committee was so kind as to give us numerics people extra time for coffee and snacks, which I think shows how much this is a valuable line of work for the community.
하시는 분 중 한 분 있어요. Yeah, this works. Yes. Okay. Yeah.
We have a great lineup of talks today. So yeah, let's go ahead and get started. Our first talk is by Niels Wundler about type-constrained code generation with language models. Take it away.
Okay, thank you. Hey everyone, my name is Niels.
and I'm presenting this work, which I co-led with Jinchuan, who's also here. Okay, and yeah, in general, it's a collaboration between our lab at ETH and Berkeley University. So, as you may have noticed, AI is being deployed all over the place because, yeah, in all kinds of variations and forms, because people find it useful to speed up code generation because, whoop, that's not what I wanted to do. Because LLMs speed up code generation because it allows people to write code even when they're not experts. And yeah, now large amounts of code bases are written by AI and so on. But actually, LLMs, even the state-of-the-art LLMs, hallucinate, make errors, especially semantic errors in code. So how can we make these LLMs more reliable? And that's what we're trying to address in this work using some proper formal systems like type systems, which we developed for humans to prevent a bunch of errors. So can we not directly leverage them to prevent a bunch of errors in LLMs or in LLM code generation? One simple approach to do this, or the direct approach, would be we treat the type system as a black box. We generate code using the LLM. We feed it to a type checker. Type checker may either say, OK, that's good, and we are good to go. We have type-safe code. Or it may give us an error and some additional information. We take that additional information, feed it back to the LLM, and then cross our fingers and hope that the LLM figures out how to fix it. This can make sense, but in general, it has the downside that we don't actually have a control over what the LLM does during the coding. We just have to hope that the LLM figures out how to fix everything. And we can have an arbitrary number of calls to the LLM that are required to actually eventually get some type-safe code. So instead, what we propose is to not treat the type system as a black box, but actually integrate it into the decoding process. The LLM generates code incrementally, token by token, and we know how type systems work. They are formally defined, so we can use them to check the LLM output during each step, and when the LLM definitely makes some mistakes and writes some unsafe code, we can steer the LLM away from that unsafe completion and send it instead on a happy path that actually type checks. So yeah, we leverage that we have full control over the decoding process. We can guarantee that when we terminate, we have some type-safe code. And as I will explain in a bit more detail, we actually only need a single pass, a single call to the LLM. So yeah, previously, type systems have been used to guide the synthetic, like a traditional code generation based on maybe trees and nodes. But what we now want is an incremental type checker that handles the token by token character level code generation. So yeah, let's see. We have an LLM, and we can use it to generate code, which is cool, just on a natural language instruction. Tell it, oh, write a function to check if a string represents an integer. And the LLM goes and writes some code. It starts with the function header and then defines some variables, calls some functions. And in particular, in the last line, it calls parseInt. This is a global function, and this is TypeScript code. This global function expects parameter of type string and will return you the integer that it represents, that the string represents. So starts and puts num, which is of type number, and then a comma. So at this point already, we know that this code can never compile. Like, it will always have a type error. But the LLM is, of course, unbothered by this and just continues to generate code. Instead, we would like a system that actually says, oh, there was an error. Maybe put toString, and now you are actually generating type-safe code. So what we need is this incremental type checker that we can give some partial program, and it can tell us, it can differentiate between, on the left side, code that we can complete to a valid program. You saw that we can put toString and we will get a valid completion. And code that is not completable anymore, it can be as little as a single character that makes the difference. In this case, it's the comma here. So yeah, when we have this incremental type checker, we can integrate it into the LLM decoding process. And on a very simple level, the LLM decoding progress just takes a partial program. At the beginning, it's an empty program. The LLM looks at the partial program, gives a probability distribution over all possible next tokens, which are just strings, like a bunch of strings, maybe 100,000 different strings. We get a distribution over which string is the most likely to follow. And then in normal distribution, in the vanilla distribution on the left, we just sample any of these tokens, append it, and continue. And what we want to do instead is leverage some checking, our incremental type checker. We sample a token, then we actually check if we can put this token next. If we cannot, then we want to sample again a different token from the same distribution and repeat until we get a final token. And we designed this incremental type checker in a way that we always remain a valid prefix so that we always can find a valid token that we can put next. This results in the setup where we actually only call the LLM the same time as before, but we just might have to do resampling here. So yeah, let's go ahead and build such an incremental type checker. We start with an automaton that helps us a bit in this construction. And this automaton is a non-deterministic automaton that only accepts well-typed programs. So whenever this automaton is done parsing our program, if it's in an accepting state, we are in a well-typed program. And this is done by basically tracking the abstract syntax tree, and in addition to the syntax tree or the nodes in the syntax tree, track some additional type information like the variables in context, the return type, and the current type of current partial expressions, and so on. So this automaton itself, as I said, it's like a compiler. At the end of the completion, it tells us whether we accept or not, and that's not yet very helpful. What we need is what we call a prefix property on this automaton, which means that for every intermediate state of the automaton, we want to guarantee that we can find a path to an accepting state. And we know that the accepting state is a well-typed program, so if we are in a state that has a path to that accepting state, we are in a state that's corresponding to a prefix of some valid program. And if there's no such state, or if we don't have a transition to such a state, then we know that we are not a prefix of any state and of any correct program, and we reject the state. Let's visualize that a bit later. First, how do we build it? We start with a generic, simply typed language, build this automaton for that. This language is a subset of TypeScript in our case, but the core type system is very similar to a bunch of different languages like Java and Go. And then we gradually extend this automaton with more and more complex features like immutable, like distinguishing immutable variables, arrays, loops, operator precedences, global identifiers, and so on. So that we can cover in the end a fairly big chunk of the TypeScript type system. Okay, so let's visualize what's going on. On the right, we have the code that the LLM has so far partially generated. On the left, we have an automaton, the automaton that we constructed. It's a zoomed-in version. This automaton is quite big. In fact, it may have infinitely many states, but we just look at the ones that we care about now. And in the center, for visualization purposes, I extracted the current type environment that this automaton extracted. So when we start, we see only some global variables. In this case, it's parseInt, which takes string, and it's a function that returns that takes a string and returns a number. And as the LLM goes and generates the name of the function, we go through the automaton as well, and then we parse the parameters. And after we completed the first line, we actually update the type environment. We get the parameter text, which is of type string, and we get the function itself is int, which takes string and returns Boolean. After the second line, we get this variable num in our context, which is of type number. And we forward a bit more again. Eventually, we arrive at that state that I described earlier, where we're calling parseInt with a variable num as a parameter. And yeah, as you can see in the automaton, we have only continuing state transitions that corresponds to well-typed completion. So we cannot put a comma because a comma would not result in a well-typed program, but we can, for example, access some members. So when the LLM now tries to add the comma, we know that there's a type conflict. We don't have a transition in our automaton, so we reject this token. The type conflict comes from, as I pointed out again, parse in taking a string and num having a number. Instead of putting this comma, which we have rejected, the LLM then infers, we sample then toString from the distribution, which is actually valid because we have some transitions in the automaton that allow transitioning there. And after this correction, the LLM figures out a correct solution to our problem. Okay, that's all nice and good. So we solved the issue that we had in the beginning. But this automaton, in a bunch of places, very straightforward. There's one situation where it's a bit tricky, and that I skipped. That I skipped over. Let's have a closer look here. So when we call parseInt and we have that part num, I told you that we want to determine at this point already whether this is a partial program or not. It may be that actually num, which is of type number, cannot be in any way converted to a string. We don't know that at this point yet. We need to solve something that's called the type inhibition problem, or at least we need to address it. And in particular, we want to figure out if there's any textual completion that can turn this type number into type string. And what we do for this is we know the type of the partial expression, we know the type of the goal type, and instead of now searching over all kinds of strings, we lift everything to the type level and we search over different operators that we can apply to types and get something like this, which is a type graph on which we can do a type reachability search. So we start from our type num, and now we search through operators that we can append on the right. For example, we can do this member access toString. This member access is finite. And we can call is finite. We recursively search through this graph until we find the desired type string. And at this point, we can determine, oh, nice, yes, we can actually turn this into a string. So this is a valid partial expression. So the whole partial code is acceptable and can become a well-typed program. There's some more tricks here, like we need to bound this whole graph to be finite to actually make sure that we terminate at some point. But we do this in a sound way so that we can always guarantee that there's some well-typed program, though we might remove some non-well-typed programs. Okay, so recap. We have this setup and we have these benefits. We have only one forward LLM inference pass, no backtracking. We guarantee the type safety once we terminate. We fully leverage this type system. And downside, we had to manually actually build all of these automata. But let's see if the work paid off. We evaluate on 6 different language models from 2 billion to 30 billion in size, 4 different language model families on 2 popular function generation benchmarks in the ML community. These are all benchmarks that require the model to write a single function, and in this case translated to TypeScript. We have synthesis, which requires the model to write a program from scratch, translation, which gives the LLM the Python translation and ask it to translate to TypeScript, and repair, which gives the LLM a previously unsuccessful run and then gives the compiler feedback. And after that compiler feedback, we additionally constrain in our type constraint system to see if we can get additional benefits beyond this feedback loop setup. And we compare then the vanilla constraint decoding with a type constraint decoding to see how many of the errors we can eliminate this, with our method. If we look, for example, at Quen 32 billion, we reduce actually the errors quite significantly, over 60% in all the settings. And this also holds for smaller models. maybe not as extreme, but we reduce even for the 2 billion model over 50% of the compiler errors. And overall, we see for all models a drastic decrease. Now, we would expect that we get a strict improvement on all of these settings because we never actually change an output when it correctly compiles. But yeah, beyond that, we can see that there's actually a quite drastic improvement here in the reduction of compiler errors. So does this also hold true for functional correctness? Before, we only looked at the at these type system errors, but we didn't actually make any statements about functional correctness, like does the program do what we want it to do? And we find that yes, it seems that we do have some improvements of several percent on all the different settings, and in particular in the repair setting, which is basically all the hard problems where the model failed on the first pass. And now, in addition to the compiler feedback, our type constraining gives even more guidance to the model to resolve these errors. And if we looked at some of this closer, and often the model just doesn't figure out how to solve the error, but with the constraining, we force it to fix the error. So in this case, we get these large improvements of like 80%, especially for the small models. Okay, so yeah, that's nice, but a lot more needs to be done. So we do not yet cover all the TypeScript features, like we don't cover user-defined classes, for example. We have constructed this now manually for TypeScript, but there's a bunch of different languages in the world, and we would like to cover all of them. So maybe for Go or Java or even more stronger type systems that give us more guarantees like Rust would be very interesting target to build such incremental type checkers. And maybe we can even generalize a bit and say, oh, there's a bunch of type systems for which we can generally, maybe even automatically, derive such incremental type checkers, whereas maybe there are some features, maybe we cannot borrow check incrementally. I don't know what Rust does. So it would be interesting to have some like more theoretical results there as well. Okay, so as a conclusion, LLMs make semantic errors and make errors during generation, but we can resolve a lot of these using an incremental type checker that's based on basically automata that parse the output during generation. And yeah, this works. We reduce compilation errors quite a lot at the end. Okay, thank you.
Okay, thank you for the talk. We have around 2 minutes for questions. So yes, in blue. Could someone give them a speaker, a microphone?
Hey, nice talk, and I'm a huge fan of this approach, and I wanted someone to do it for a long time. But the question I have basically is, have you considered exploring not just one pass tree autonomon, but like a search tree of possible paths to find somehow better solution? Because I assume, let's say, LM generates an output, right? But there are many possible outputs if you don't pick only the first most probable, but maybe 1, 2, 3, I don't know, small number. Yeah. You can explore some small exponential subspace.
Yeah, there's some, I mean, I've considered this, and there's some very rough work in progress with the student on this. But essentially, we found that, like you can basically do this tree, and then you maybe need to actually give the model some additional context on why some trees are wrong, because it often converges even in different branches of the tree to make the same error again. Yeah, but you could also combine this with beam search or any other basically search algorithm, and it should work. Yeah. Thanks for the question.
One more question. Yes, and over there in white. I know there's lots of questions. Maybe you can find the speaker after.
Yeah, thanks for the great talk. And my question is, you only considered one type system. And I think the type system of TypeScript is quite coarse. That is, any number is a number and any string is a string. But when we think about a Rust type system, there is a bunch of other, various types of strings, and there are a bunch of other kinds of numbers, and like integer 32-bit and 64-bit. So my question is, when we are implementing this strategy to the other more fine-grained type system, do you think it's going to guide the LLM like this well, like this approach?
I think so. Like even in TypeScript, we implemented some kind of like type super subset settings, and basically you have this in integers, right? That you have the numerical constants, maybe a super type of all the different lower, like finer grained integers, and if you add, yeah, I think this kind of support should be addable to this. So no guarantees.
Okay, great. Let's thank our speaker one more time. Okay, so our next talk will be a recorded talk by Shangwei Wang from North Carolina State. He will be available on Discord after the talk to answer some questions. So we'll get that on the screen shortly.
Hello everyone, my name is Shangwei Wang, a second-year PhD at North Carolina State University. It is my honor to present our work, Reductive Analysis with Compiler-Guided Language Models for Input-Centric Code Optimization. Our work is inspired by the fact that input adaptive optimization is important for many fields. For example, in the serverless computing area, they have a job controller to assign jobs to different computing resources. For a certain program, different inputs need different resources and take different costs. Input adaptive approach will guide the job controller to save resource usage and cost. From our experiments, we noticed nearly 65% resource reduction compared to input oblivious approach. Input adaptive optimization are also helpful in other fields. Previous research showed that input adaptive approach can bring 10% to 26% speed up for just the in-time compilation, achieve 1.5 to 2.5 times performance improvement if selecting the more suitable garbage collection based on inputs, and up to 1.47 times speed up on a set of GPU applications. In the previous work, researchers proposed a three-step workflow for input adaptive optimization. In first step, it needs to extract the important features from program inputs. In second step, it builds the machine learning model from those features to predict program behaviors. Finally, it adopts model for different optimization targets. Our focus is on the first step. So why is it difficult to do input characterization? It is because inputs to a program are often complex. Take a hurricane prediction software as an example. The inputs to the program include satellite images, data collected by weather balance, various ocean data, and so on. It is hard to directly tell what parts or attributes of the input critically affect the speed of the program by only paying attention on the inputs themselves. This is because the significance of each type of the inputs are decided by how they are used in the program. Therefore, to analyze the effect of the input, we need to focus on the program. Input characterizations is hence a program analysis problem. Previous work tries to give a systematical solution by analyzing statistical correlations among program behaviors. It needs to collect a set of inputs for a program and test the instrumented program with these inputs under several runs. Through this process, the instruments collect massive profiling logs for many program behaviors, such as the conditions and loop trip counts. Then they did a statistical correlation analysis on these program behaviors to obtain a similar behavior, which are defined as behaviors in a program that are strongly correlated with many other behaviors in the program. and meanwhile expose their values early in typical executions. They will be used as the representatives of the input features for the program. However, this approach still has some challenges. It is tedious and time-consuming due to detailed profiling runs and extensive correlation calculations. For program, it may take 4 to 404 hours to gain those data. Therefore, it is hard to be integrated into compiler workflow. By analyzing the prompts and the counts of large language model and compiler, we think it is a promising future to combine large language model and compiler together to solving the limitations we mentioned before. Most notable is that large language model can capture high-level code semantics, but faces scalability limitations. When it was used to deal with large code bases and give reliable code analysis results. The basic hypothesis of this work is their combination in form of compiler-guided large language model provides a solution to automatic input characterization. We mentioned that large language model has scalability limitations. Now I want to dive deeply to this problem and give our strategy. The limitation comes two dimensions. The first one is the program behaviors. One type of program behavior, such as execution time, is composed of the behaviors of almost all pieces of the program. The behavior complexity grows as program code size increases. Our strategy is to reduce the focus of analysis from all pieces to a much smaller set of behaviors, named the similar behaviors, and then map similar behaviors to input features. Similar behaviors are a concept introduced in previous work. The second dimension is code size. We all know that the current large model have a limit on the maximum number of tokens for request. Even the limit becomes larger and larger, large language models still show poor performance on long contact. Thus, it is meaningful to instruct large language models to focus on a certain scope when we try to use it on program analysis. Our strategy is to use call graph to get a larger model to conduct similar behavior analysis on one function at a time. This is the overview of our Numeric design. It has 3 parts. The first part is the preparation process to prepare the inputs for the subsequent analysis. The second part is the RCL code analyzer. It follows a reductive algorithm and a set of well-crafted prompt templates to enable large language model analysis through the call graph. And the final part is an extraction module creator, which creates a code script to extract input features from the new inputs. To help you understand what is going on in the RCL code analyzer, I show part of the running example here. The entire example is in the paper for you to read. We are dealing with a function on the leaf named power. This is the power function. We provide the info side of this function to a large language model. It responds the analysis results, including similar behaviors and input influence. The input influence of this function is none because this function doesn't use inputs from the entire program directly. This analysis result is added to the info side of its caller function. And since its caller function only has one calling, that caller function is ready to be processed. So it is added to the process queue. One case inside is we need to carefully design the propagation between the functions. We represent the information passed from the callee to the caller in the analysis results. It includes 3 parts. The first part is similar behaviors with auxiliary information. This information includes a reason. The reason is why to choose a variable or a program behavior as similar behaviors. And another part is position. It means where these program behaviors are. For a function, the similar behaviors might be in the function parameters. Maybe it comes from a global variables, or it just local variables inside this function. The second part is input influence. It includes the order of input reading and what is the program input influence to the values in the function. This pieces of information is to record how program inputs take effect directly on the program. And it will be used for input mapping in the further analysis. The third part is the return value. It records how the return variables get these values. We store this information to avoid infer loss due to the value escape. Our analysis is based on the call graph. If the program contains hundreds of functions, we might be concerned about whether the analysis results will be accumulated larger and larger until exceed the token limits. We rely on the internal large models to automatically filter and prioritize similar behaviors during the analysis process. But to help larger model in that process, we embed some generic instructions in the prompts. One is that if a similar behavior in the callee function corresponds to a function parameter, large language model should replace its reference with a corresponding variable in the caller function. This ensures that behaviors are propagated meaningfully through the call graph rather than just repeated. The other one is we ask the large model to explain why a behavior is chosen as seminal by providing a justification in the reasoning field of the response. This explanation mechanism enforces internal consistency in large models' reasoning and encourages it to prioritize behaviors that are more fundamental to the program performance rather than just have some surface level correlation. When the analysis reaches the root of the call graph, such as the main function, it does the similar behavior analysis as usual, and then maps the similar behavior to the features of the program inputs. Here, the similar behaviors are already represented as for the entire program. There are some other highlights I want to briefly introduce. Recurrence is an inherent barrier for the reduction on call graph because recurrence forms a third cycle, which prevents the reductive scheme. Our solution is to break the cycle but has key info preserved with the help of a larger model. Specifically, it repeatedly removes the edge in a recursive cycle that points to the function that has the lowest index until no recursive calls remain. But before breaking a cycle, it first uses the larger model to figure out the termination condition of the recursion. Termination conditions are considered as the representatives of the recursion and are included as extra information in the further analysis. The second is the extraction model generation. We use the larger model to generate the model based on the input feature analysis. This model can be inserted at the beginning of a program. When a new input comes, it extracts the features from inputs and utilizes machine learning model to achieve input adaptive optimization. In this work, we use XGBoost because it is light, scalable, and efficient. And our work is based on a set of well-crafted prompts. We find that the quality of prompts is critical for the performance of large language models. We employ several prompt engineering techniques to design these prompt templates. They are all open source in our paper or artifacts. To prove the efficiency of our work, we evaluate on 3 use cases. We use the traditional profiling-based method and the large language model-based MapReduce method as counterparts. MapReduce method is a standard approach to deal with the token limit for the large language models. We use GPT-4 and DeepSeek v3 as the large language model backend. We use 10 programs for our evaluations. Our benchmark includes 4 real-world applications with 1,000 to near 100,000 of lines of source code and 10 to hundreds of functions. Their size all exceed the token limit of larger model GPT-4, making them suitable for testing scalable solution proposed in this work. We collect 25 to 256 inputs for each of the programs. During the collection, we try to ensure that the inputs are typical in the normal executions of the benchmarks. The results compared the time needed for the input characterizations shows that we can achieve 450 times speed up because we avoid time-consuming profiling and calculations. Well, we can also get even better time prediction thanks to the excellent code analysis ability from large models. On the serverless computing test cases used our method, the scheduler can achieve input adaptive optimizations, resulting in 33% higher SLO hit rates and 65% resource reductions. The SLO hit rate is a serverless level objective latency hit rate. The benefits are obvious in the OpenMP parallelism optimization as well, with 90% accuracy in selecting the appropriate adaptive decisions and achieve 15% speed up. On shortest job first scheduling, input adapt can achieve 7 times speed up, close to using the true chain. For our conclusion, we think first we propose the first known exploration on leveraging large models to clear barriers for identify critical input features for input-centric program optimizations. We combine large model with a novel reductive scheme can effectively address the scalability challenges to large model for code analysis and optimizations. We think compiler-guided large model have promising potentials to solve traditional programming problems. Thanks for listening. Feel free to ask me questions. Thank you.
Okay, let's see. If we're able to get some correspondence on Discord, we might take a question. Did they say they're available? Okay, good. Can they hear us? Hi, Zhangwei, can you hear us? If you can wave or slow delay. Okay.
Yes, I can.
Okay. So there's going to be around a 20-second delay. We had this earlier, so maybe we'll take one question from the audience. Any question from the audience? Okay, so in this case, I have a question. So what would you say are, for the future work, what is the main area you'd like to focus on?
For this work, we may want to introduce some more scalability issues because currently we only focus on one function at a time, but it actually still costs some money and time to finish a very big picture. So we aim to propose scalability solutions to group functions together and to analyze entire call graph group by group to speed up this analysis process.
Sounds great. Okay, I think we don't have much time for another question, so let's thank our speaker one next time before we move to the next talk. Okay, yeah, let's get ready.
Okay, cool, thanks. It's not working.
Hey, they'll get that set up.
I'm trying out.
Yes. He still doesn't see the screen.
Yeah, I did.
Okay, great. So for our next talk by Han-Lang Zhang and collaborators about scalable, validated code translation of entire projects using large language models. So please get started.
Hello, everyone. I'm Han-Lang Zhang, a PhD student from the University of Bristol. I'm very glad to present here our work, Scalable Validated Code Generation of Entire Projects using LLMs. This is a joint work with AWS, and my collaborators are Christina and Mon from Bristol, Brendan and Daniel from AWS. The background of this research stems from the industrial need of translating security-critical code bases into Rust. Specifically at AWS, we encounter practical need to migrate several Go code bases. While there exist works that rely on symbolic techniques for automatic code translation, the code produced by such tool is often not idiomatic, and thus less maintainable. As a result, we proposed to develop an LLM-based tool for translating existing Go source code into Rust. However, real-world code bases are often of large code size and are organized into complex file hierarchy. While LLMs have shown their power of producing good quality of code, the limitation of context window block us from translating whole repositories all at once. To scale up, the general approach we follow in this work is to modularize the translation query. A repository is partitioned into individual translation units, like a function, a type, or a global variable. These code fragments are then translated by the LLM following the dependency graph, producing code fragments in Rust, which are later on combined into an entire project. However, being modular is not sufficient in itself. When applying the modular translation algorithm, two key challenges arise. Firstly, we discover that LLMs are often unreliable when translating features of the source language that do not have a direct mapping to the target language. For example, in this Go program, a global variable x is initialized by calling a function. Without specific instructions, the LLM can produce Rust code that largely simulates the syntax of the Go program, where the static variable is initialized by directly calling the function as well. However, this is invalid in Rust as static variable can only be initialized by constant expressions or constant functions. Therefore, this default translation could not compile. There are multiple ways to salvage this translation. For example, one could rely on the lazy construct from a standard library, which supports lazy initialization and therefore allow initialization by calling functions. Similarly, one could rely on third-party libraries that provide the same functionalities. And there are perhaps many other solutions. While the LLM can sometimes generate correct code fragments, it is not guaranteed that these fragments consistently use any of the solutions. To resolve issues like this, we propose a technique called feature mapping that incorporates predefined high-level translation rules with LLM's code generation. These rules specify how particular source language features should be mapped to constructs in the target language and allows for customization. This approach improves both the compilation success rate and the consistency of the generated code. Secondly, it is challenging to validate the translation in terms of semantic equivalence. Since we translate the program modularly, we aim to measure semantic equivalence at the function level. Here we assume that the Go program comes with a suite of unit tests that achieve high functional coverage rate. While these unit tests can be used as specifications of the original functions, it is not obvious how we can transform these unit tests into the functional specification of the translated Rust functions. It is especially challenging when the function signature involves non-primitive types or user-defined types. as LLMs may generate code that contains types that are not compatible with the original source code, meaning that the runtime values witnessed by executing the unit test cannot inhabit the ROS types. In this work, we propose a technique called type compatibility check, which dynamically checks that a Go type and the ROS type can safely interoperate, allowing differential testing of the translated ROS functions. We incorporate the two proposed techniques into the modular translation workflow. Before starting the translation, we collect execution snapshots for every function in a source project. Execution snapshots are a pair of input-output examples that serves as specification of the function to be translated. For each partition code fragment, we construct feature mapping prompt that specifically instruct the LM for target features, obtaining a candidate ROS code fragment. And this fragment is then statically checked against the corresponding feature mapping rule and dynamically checked for type compatibility by using the execution snapshots. If any of the checks failed, we recreate for a new translation. We set a finite budget on the number of regeneration to avoid infinite loop. We call this translation process a type-driven phase. After type-driven phase, we obtain a type-compatible project translation, and we apply an additional semantic-driven refinement phase. We run the oracle constructed for all functions. If any of the tests failed, we requery for a new translation with signature frozen. Again, we set a budget to prevent infinite loops. After all functions are refined, we combine all the code fragments to an entire project as the translation of the original project. Now we'll go into details of our two techniques. The first technique, which we call feature mapping, comprises predefined high-level translation rules for prompting and checking LLM's code generation. For the code snippet containing the global variable initialization, as discussed before, we apply this particular rule. Note that for clarity, we summarize our predefined translation rules by using a slightly non-standard inference style rule. We first check the shape of the source code, which is a global variable initialized by a function. Then we construct the prompt to specifically instruct the LM to use the lazy construct. While doing so, there's no guarantee that the LM will actually generate the code we want, or even any code that makes any sense. We therefore apply static checks on the generated code to enforce the rule that the code is indeed a static variable initialized by the lazy construct. Note that we don't impose any additional constraints, and the LMs are even free to generate names of the global variables. This is for idiomaticity purposes, as Go prefer camel cases, where ROS prefers snake cases. Now, if the check failed, we give out the current translation and requery for another one. Once obtaining code fragment that satisfy the desired pattern, we perform post-processing, which is not necessary for this simple case. So in summary, a feature mapping rule comprises three parts: a specific instruction in the prompt, the static checks that enforce the rules, and necessary post-processing steps to instrument the code. Of course, there are many other differences in features between Go and Rust, like error handling mechanism, where Go uses error return value, and Rust uses result enumeration. Also, there are huge gaps in programming abstractions where Go uses structural interface and Rust apply nominal traits. These challenges can also be handled by our feature mapping rules. We have rules that map a fallible Go function into a fallible Rust function by requesting and checking the usage of result enumeration and a specific error type called anyhow error, which is a third-party dynamic error type, allowing casting between dynamic error, simulating common coding patterns in Go. Note that these kind of rules allow for customization. The user can choose different error types to map into and modify the rules and prompts accordingly. Also, we have rules for systematically and modularly map an interface and its implementations to a Rust trait and implementations. Note that this rules requires post-processing of the code generated by the LLM in order to preserve potential sub-interfacing relations. For detailed description of these rules, we refer to the paper. All these rules contribute to higher compilation success rate. Also, by applying these predefined translation rules, we have a very clear understanding of the code generated by the LLM, which facilitates manipulation of such code. For example, combining code fragments with other fragments, constructing oracles, etc. After obtaining candidate function translation, we need to consider constructing an equivalence checking oracle. We follow a differential testing approach. We first execute all existing unit tests for the Go project to be translated. For every function covered by the unit test, we collect execution snapshots, which are pairs of function input-output values. These input-output values are then ported into the Rust program by using serialization and deserialization, where we construct a test harness such that we execute the Rust function with input values from the execution snapshot and check whether the Rust output equals to the output values from the execution snapshots. Note that these steps requires that the input-output types from both sides need to be compatible or interoperable. Additionally, we model side effects such as global states, input states mutations, which are omitted in the above diagram. In our experiments, we noticed that sometimes LLMs generate translations with incompatible type, which lead to incompatible function signatures, causing the equivalence checking oracle to crash. For example, consider this Go function that takes a slice of string as inputs. The LLM can generate a plausible translation, which is a function that takes a vector of string as inputs. This translation is incorrect because upon checking execution snapshots, we found that the null value has ever been an input value to this function f. However, null value does not inhabit the Rust type vector of string. Recall that we differentially test a Rust function by porting Go values into Rust by deserialization. This process is doomed to crash at runtime. As a result, we devised the notion of type compatibility, which says that any feasible values that can inhabit a type in the original Go project should also be able to inhabit the corresponding type in translated Rust project. Type compatibility ensures the equivalence checking oracle can be constructed without runtime crashing and can filter out wrong translation early. During the translation, we enforce type compatibility check. For the previous translation, we look at the function signature and found that the input type is not compatible with the original input type, as it does not permit the null value. Thereby, it is rejected, and we proceed to recreate for a new translation. Now, the input type of this new translation is wrapped by an optional, and therefore null value inhabit this type, and so does any other values. This time, the function signature is type compatible, and we accept it and proceed to later phases of the translation. To evaluate the efficiency of our approach, we select 8 real-world code bases as benchmarks, with size ranging from 300 lines to approximately 10,000 lines of code. We target at popular code bases, and we believe that popularity reflects idiomaticity of the code base. Also, we select benchmarks that are with unit tests of high functional coverage rate. Our experimental evaluation shows that our approach achieves very high compilation rate for the benchmark selected. Measured by the percentage of function translated that successfully compiled, we achieve an average of 98% of success rate. Our approach also shows a relatively high input-output equivalence rate, similarly measured as the percentage of function translated that successfully passes our oracles. We achieve an average of 73% of success rate. Also, the translation consists of 100% of safe code. We also ran an ablation study where we don't apply the feature mapping techniques, and the success rate drops drastically. Without feature mapping, LLM may produce code fragment that fails to compile, or fragment that is in conflict with other fragments, causing the translation loop to halt quickly. We also ran an ablation study where type compatibility checking technique is removed. We noticed a drop in the success rate due to translation that have incompatible types. So as a conclusion, in this work, we developed a scalable Go-to-ROS translator that can produce validated code. We propose two techniques, feature mapping and type compatibility, that can improve the quality of the translations. And you can find our public artifact at this URL. And a public GitHub repository is coming out soon as well. And that's so much for my talk. Thanks so much for listening, and any questions are welcome.
Thank you. So yes, we have a question. Yeah, in blue. Is there? Yep. You give them the mic over there, please.
Hi, Milind Chabi from Uber. Interesting work. Can you speak about how you are handling concurrency and transforming Go code to Rust code, both shared memory and message passing?
Thanks. That's a good question. We don't handle concurrency at this moment because that's a really hot feature. We believe that if there is a chance of defining like high-level translation rules saying like current like specific concurrency primitives can be translated into like corresponding ROS primitives or a combination of ROS primitives, then we might be able to do the translation. But for now, we don't consider concurrency.
Another question, how about, how are you handling library calls?
That's a great question. So the benchmark we selected only relies on standard libraries or libraries of well-known third-party libraries. And typically, LLMs have the knowledge of selecting the corresponding library APIs, and we have an ongoing work that kind of extend the current framework to handle like arbitrary third-party library by using some ragging techniques. So yeah.
Thank you.
Good. Another question over here, please, the front.
Hi. I wonder how you check the equivalence of the two codes. Why the Rust code is considered as the correct translation of the original Go code.
Yeah. Thanks for the question. As discussed in the previous slides, we kind of construct oracles by using existing unit tests from the Go repository. So basically, what we do is that we execute all unit tests from the Go repository, and we collect execution snapshots, which are kind of like input-output examples for every function in the Go for the Go functions. And by using some introversion techniques, we kind of ported this input-output example into Rust and use that as the specification for the function translated.
Okay, we have time for a question. You have a question? Okay, yeah, let's ask a question from here.
Thank you for the talk. How do you handle borrow checker? How frequently did it happen that the borrow checker rejected the translated program?
Okay, thanks for the question. So we don't particularly handle borrow checker. We kind of rely on the LLM to generate correct code. But as you said, the borrow checker of Rust is very strict. It sometimes produce compilation errors, and we do encounter some hard cases where the original Go code is written in a really, I would say, not rusty pattern, like you use share mutability, share ownership, and all that stuff. And such function cannot be translated. So, yeah.
How frequently did it happen?
In our benchmark, it happens not so frequently. Like most of the code are translated just fine. So.
Okay, we have time for one more question. Maybe right here in the second row. And in the meantime, if the second speaker can get ready.
Okay, so I want to argue that relying on the unit test as the ground truth is both expensive and so limited. So any idea on how to fix it?
Yeah, thanks for the question. So we have tried fuzzing as well. So basically, we can construct fuzzing tests on the Rust side. But the problem is that the input example generated by the fuzzer is of less quality than the example coming from the unit test. And we've also have some previous work try formal methods and by using model checker and all that stuff. But the question is that they don't scale up to the level of, say, 10,000 lines of code. So currently, we found unit tests being our best option but we're also exploring by using, say, like better fuzzer or stuff like that. Yeah, thanks.
Okay, let's thank our speaker one last time. Okay, and so now we're at the last talk of the session with Yixuan Li, who's going to present his work on guided tensor lifting.
Hello, everyone. Welcome to my talk. This is the last talk of the day. My talk is about guided tensor lifting. My co-authors are Jose Wesley de Souza Malinhais, Alexander Brockman, Michael Boyle, and Elizabeth Pogorin. First, let me introduce you program lifting. Previously, all code worked on all hardwares. And if the hardware got faster, your code got faster automatically. Hardware is now becoming more specialized with corresponding DSLs. TPU, GPU, AI accelerators, they all ship with their own DSLs. And using this specialized hardware gives performance gains. In machine learning worlds, machine learning workloads are dominated by tensor code. And the key to efficiency is the highly parallelized algebra. DSLs like Taco make this easy for new applications. Taco is the tensor algebra compiler, a fast and versatile compiler-based library for sparse linear and tensor algebra. Okay, we can now write our new applications with new DSLs, but what about the legacy code? Do we need to manually lift C to Taco or PyTorch or NumPy, or manually rewrite MLR to JAX, or manually lift C++ to Collide? Do we need to do that? That's painful for millions of lines of legacy code, right? So can we automate the process of language lifting so we can just lay down and play our mobile phone? We're focusing on lifting C code to Taco code, but there are lots of other DSLs that this work could apply to. First, let's look at an example. This is a legacy C code. What it's doing, it is doing a dot production. That one. And the corresponding Taco expression in Einstein notation is AI equals to Bij times Cj. Taco expression can then be compiled to highly parallelized dense algebra. The Taco speedup for our benchmarks will be 1.79 times on the multi-core platform and 24.1 times faster on the GPU compared to the previous legacy C code. What can we do for the automated program lifting? Maybe we can use program synthesis. Program synthesis is the task that automatically finds a program which satisfies a specification. And here in tensor lifting, specification is the legacy C code. And the grammar to guide the lifting is the Taco grammar. But we are facing problems. This is the Taco grammar, part of the Taco grammar. It is long. And search space grows exponentially as the programs get longer. Thus, the synthesis time grows to infeasible levels. So what shall we do? Maybe, yeah, try LLM. LLM code generation is fast and scale with program complexity, but it also has a problem. What is that? Hallucination, right? So there will be two questions. What if LLMs produce plausible-looking yet fundamentally flawed solutions? Maybe you'll try again. We sample 10 times. And how can we still use LLMs despite hallucinations? We treat LLMs as tools for ideas, not guarantees. That is our chance. So the answer for those two questions is we can combine LLM with an enumerated search from program synthesis. So our pipeline will be something like get solutions from LLM and generate probabilistic grammar. Then we guide enumerative synthesis with the probabilistic grammar. This is a figure of our pipeline. We can split it into 4 parts. LLM part, guidance, search, and verification. Let's go through our first part, LLM part. If we have an input C program, we can prompt our LLM to get 10 possible solutions. This is our prompt. We say, you are a scientific assistant that knows a lot about transpilation. Translate the following C code to an expression in the tackle tensor index notation. The expression must be valid as input to the tackle compiler. Return the list with 10 possible expressions. Return the list and only the list, no explanations, followed by the input C program. And we will get something from LLM like this. This is the response. Now let's move on to our second part, the guidance. Actually, there are 2 small parts in the guidance. One is the probabilistic grammar on the top. We need that to generate the right-hand side of our tensor probabilistic grammar. And another on the bottom is the dimensional analysis. We need it to generate the left-hand side dimension. Why do we need 2 parts? Because LLM, it doesn't know the left-hand side. We tried it. It just doesn't work. So we need 2 parts, one for the right-hand side and another for the left-hand side. Let's go back to our example. For the left-hand side, we need to determine this one, AI. So how do we determine the left-hand side tensor? First, we look for main assignment. What are the main assignment for this input example? These 3 lines, they are the main assignments because only PT increases in those 4 loops. And PT is initialized to result. Then we count the number of loops controlling pointer increment, which is the PT. We just find PT, these 2 lines. That is a single loop. So we can say it represents a 1D array. Thus, we can rewrite our left-hand side from int star result to AI. Now let's move on. If we have a result like this, actually, line 1 and line 3, they're identical if we normalize it to the middle one. Actually, the middle AST, the middle tree. AI equals to BJI times CJ. And according to guided enumerative program synthesis with large language models, our previous paper accepted at CAF 2024, we can extract a probabilistic grammar from the LLM's response. But using a grammar of templates is different from the CAF work. Convert a set of LLM-generated tensor expressions into a grammar that captures the likely space of the correct solutions. And the frequency of each pattern in LLM solutions indicate its likelihood of being correct. This is the grammar for all ISM expressions. And this is the grammar for ISM templates with holes. What we need is to fill those holes with probabilistic grammar. If our response is something like this, we can have a probabilistic grammar like this one. The line 2, tensor 1 defines as AI, and the probability with 1 is from left-hand side, the dimensional analysis. And the rest of them, line 3, line 4, and line 5, that the right-hand side comes from LLM solutions. Okay, now we have finished the guidance part. Let's go to our search part. If we add the search engine here, we can finally have a pipeline that looks something. We can get a candidate. In our search engine, we're using A* enumeration. It chooses paths based on minimizing path score. And the score is the cost so far, plus the estimate of cost to complete the program. And the costs are calculated from the probability. Let's have a very easy example. If this is our grammar, we first initialize the queue with the start symbol E. And here's the queue stores partial programs with scores. We have E, and we pop the partial program from the queue with the best score, which is, now it is E. We pop it, and then we expand it. We can expand it to T and E plus E. We update the queue. It is updating. And we pop the partial program from the queue with the best score. E plus E can be expanded to E plus E plus E and T plus E. Then we update the queue. It is updating now, yeah. And the highest score partial program should be T. We pop it, and we expand it to A and B. Now we update the queue again, and we pop the partial program with the best score, which is A, but actually A is not a partial program, it is a complete program. So now we have a candidate. We can verify it. Before verifying it, let me introduce our two different enumerators. The first one is the top-down enumerator. If this is the LLM response, we can use the top-down grammar to guide the top-down enumerator. The top-down grammar looks like this. Top-down enumerator expands from the root symbol downward, and it naturally handles nested or deep expressions. The estimate cost at node X is the minimal additional cost required to complete the partial expression to a full expression. And another is the bottom-up enumerator. This is the grammar to guide the bottom-up enumerator. It builds expressions from smaller sub-expressions upward, and it finds short expressions quickly. The estimate cost at node X is the minimal additional cost required to build an expression with the predicted length. And the length, it comes from the solution, the LLM solutions. Okay, now let's go to the final part, verification. It contains two steps. The first one is validation step. If the candidate succeeds, we can move to the second step, the bounded model checking step. For the validation step, it is an IO check. It checks if a synthesized taco expression can produce a program equivalent to the original C code based on input-output behavior. The process is like we generate IO examples. We run the original C code on random inputs to get expected outputs. And then we instantiate the taco expression. We try all valid substitutions of the tensor and constant symbols. Then we run each instantiation on the inputs. We only accept taco candidates if output match. Then we go to the bounded model checking step. It proves that two programs are equivalent up to a bound. The process is we lower both programs to MLIR, both the C, the original C, and the generated taco. The taco expressions, it uses JX plus NumPy to emit MLIR. And then we compile them to C with assertions. We assert equality of outputs for all inputs up to a bound. And for the bounded model checking, we use CBMC plus CVC5 to verify the assertion holds. These are our benchmarks. We have linear algebra benchmarks, machine learning, image processing, signal processing, math functions, array programming, and we also contains 10 artificial, which we made it ourselves. Here are our baselines. The first is the previous state-of-the-art, C2TACO. It is a synthesis tool that generates TACO code from IO examples. It implements a bottom-up enumerative algorithm without guidance. And another baseline is also a previous state-of-the-art synthesizer, TenSpiler. It uses intermediate language, TensIR, that expresses tensor operations. And TensIR enables lifting, verification, and code generation. Okay, let's look at our results. For the percentage of coverage, the LLM, it can solve 44% of benchmarks, and the previous state-of-the-art, they solve 78 and 87. The best is our top-down enumerator. It solves 99% of benchmarks. And yeah, we win. And for the synthesis speed, let's set C2TACO as baseline. TenSpiler is 5 times faster than C2TACO. Top-down is 7 times faster than C2TACO. And the fastest is bottom-up. It is 12 times faster than C2TACO. Double win. And this is my talk. I'm on job market. Here are part of my first author papers. If you need to find an expert in LLMs and code generation, code lifting, please go find me. I'm on job market. My name is Yixuan Li from the University of Edinburgh. Thank you very much.
Thank you for the talk. So we have 3 or 4 minutes for questions. I imagine there are a lot of them. Okay, one question.
Thanks for the great talk. So can I know benefit of top-down method compared to bottom-up? Because as far as I remember, the top-down method is a little better than bottom-up method.
So your question is about why top-down is better than bottom-up, right? Yeah, because our benchmarks contains nested expressions, which means there are parentheses, like A plus B with a parenthesis and then times C. But a bottom-up enumerator, it cannot build such expressions because it built from smaller expressions and merge them together. It cannot do that. That is why top-down is better than bottom-up. And maybe if you ask about the synthesis speed, because bottom-up, it searches from smaller expressions and then to the longer, so it will find the expression, the solution first, because the solution might be smaller.
Another question? Yep.
Thanks for the great talk.
Thank you.
I want to hear about the other, a more complex example, because the Einstein sum, that was the example of the talk, but it was pretty simple. That I think that just LLM can solve the problem. So do you have any good example that can show the effectiveness of this approach to solve some more complex expression that TACO can express?
Okay, if you want to solve more complex expression, you can find our previous paper, CAV'24. That is more complex than this one. You can go read that paper.
Okay. Yep, in the back over there, there's a question.
Yeah, thanks. Maybe a bit as a follow-up to that.
Yeah.
So you had 99% in the top-down. Can you talk about the 1% that you couldn't solve? Like, is there an example of one that you couldn't?
Oh, that one is the hardest. It is long, and our timeout is set as at 1 hour. If we extend it to 2 hours, we can solve it.
Okay. Let's thank our speaker. One last
Thank
time. Bye-bye. So that's the conclusion of today's session. I think, yep, we're done for the day. There's some more events in the evening, so feel free to enjoy the rest of the day.